One and all, and we are going to start our inauguration session. I kindly request if you have any problem in connectivity or any issue, you can write on chat box. We will try to resolve your problems. With this, we are starting our event. Respected speakers, head HRED, workshop coordinators, faculty members, participants, and my dear friends, a very good morning to all of you. Today we have gathered here for international workshop on solar thermal energy storage. I would like to extend a warm welcome to each one of you on the behalf of organizing team of this workshop. Thank you all for joining this event virtually. I'm sure you will find all the session highly interesting, informative, and helpful for further research work in this field. As highly experienced and knowledgeable international academicians are connected with us here today. Light and brightness has always been equated with positivity, motivation, and harbinger of good. With this auspicious note, I, I now request all the dignitaries and speakers to permit us for virtual lamp lighting and inaugurate the event. Thank you so much. And now I would like to request Professor R.P. Saini, coordinator of this workshop, to give welcome address and tell us about this event.
Thank you, Siddhita, and very good morning, all of you. Professor Aski Singhal, Head of the Department of Hydro and Renewable Energy, IIT Roorkee, distinguished speakers, chairperson, and rapporteurs of the different sessions, dear participants and my colleagues, it is my utmost pleasure to welcome you all in this inaugural session of this international workshop on solar thermal energy storage. As we all know that the solar energy is one of the most adopted renewable energy resources due to its abundant availability and eco-friendly character. However, there is a need to manage few technical obstacles like low efficiency, hindrance in continuous energy supply, and monetary this impedance for its sustainable development. In order to continue energy supply, the solar energy systems require an effective energy storage technology to store the energy during its availability and deliver it on its requirement. We know that the solar energy can be tapped or can be utilized in two different routes. That's a direct conversion into electricity, and another is the we can use the solar energy in the form of the thermal applications. Accordingly, we need two different type of storage of the solar energy. So for solar thermal energy system of different temperature ranges, the energy can be stored in thermal energy storage system. That means this storage, especially in thermal energy storage, we have, that means there are so many issues related to the solar thermal energy storage. The present workshop is planned with the aim to bring together the experts from academia, industry, corporate, volunteer social organization, government agencies, and other related sectors on common platform to discuss the various aspects of solar thermal energy storage system for its development and effective utilization of the society. It is the honor of Department of Hydro and Renewable Energy in Indian Institute of Technology, Roorkee, and privilege in organizing this international workshop on solar thermal energy storage in India. A total of more than 400 participants from different industry, academia, government organizations, and manufacturers from India and abroad have registered to participate in this workshop, which we consider the huge number, the huge participation. Among all the participants, more than 50 participants are joining us from 13 different countries. Nearly 100 participants are from different private and government organizations, where more than 250 participants are from academic, including foreign universities and IITs, NITs, government industries, and private universities. The workshop is planned for 2 days with 5 different sessions. The first 2 sessions are scheduled on the first day and include 3 speakers from foreign countries and 1 speaker from India. The speakers will share their wide experience in the field of solar thermal energy storage. The second day of the workshop include 3 sessions in total, and the first 2 sessions include 6 speakers, including 2 from foreign and 4 Indian speakers. The last session of the second day is proposed to have panel discussions with experienced panelists on the various topics covered during the previous sessions. This session will provide the key outcome of the workshop and will draw the different recommendations which may be useful for further development of solar thermal energy storage technology covering different aspects. The last, I would like to thank all the participants for giving overwhelming response. The participants, I'll ensure that they will be provided to the certificates for joining this workshop, and I wish all the best and thank you. Thank you, Siddhita.
Thank you, sir. And now I would like to request Professor S.K. Singhal, Head HRED, IIT Roorkee, to share his valuable remark about this workshop.
Thank you, Siddhita.
Thank you, sir.
Professor R.P. Saini, coordinator of this workshop, other dignitaries, faculty colleagues, participants, and dear students. The Department Hydro and Renewable Energy at IIT Roorkee, formerly known as Alternate Hydro Energy Center, was established in the year 1982, and this year we are celebrating its Ruby Jubilee year. So such events becomes important. And about the details of this workshop, today's workshop on solar thermal energy storage has already been told by Professor R.P. Saini. And the importance of this workshop is because solar energy can be effectively utilized with various solar thermal applications, and also resulting in the advantage of energy conservation and
on the concept that the best alternative should have the shortest distance.
Now, in the present scenario, it is necessary to adopt the solar thermal applications in a small as well as large scale energy requirement. And this is for the sustainable development and also for welfare of future generation. The advancement of solar thermal energy storage is one of the major steps for moving forward in this path. This workshop will provide a common platform for sharing the experience, discussion, deliberation, and way forward for the future. So I will not take much time, and I congratulate Professor R.P. Saini and his team for timely organization of this workshop and wish a grand success to the workshop. This time, to compulsion of this pandemic, we are meeting virtually. Maybe in future we'll plan some such events where we meet physically. Thank you all and best wishes.
Thank you, sir. And now I request all the participants to turn on their camera for the snapshot for the inauguration session. Then we will move forward to the our first session of the day. Thank you, everyone. Now we will start with our first session, and the chairman of the session is Professor.
Siddhartha, we can wait for, because we'll start 5 minutes before the thing.
Okay, okay, sir. We will start our session within 5 minutes. Dear participants, we will start our first session at 10:30 as mentioned in schedule. You can, if you have any problem regarding connectivity or certificates or anything, you can write on chat box or you can ask on WhatsApp group.
Hello. Good morning.
Yes. The certificates will be provided on the basis of your attendance for 2 days. And if you will not get the certificate after within a week, then you can contact us on our official mail ID. We will provide the certificates to you all. We have copied the link of the WhatsApp group, so anyone, if they are not added in that group, you can join the group. So you will get all the further information regarding the workshop timely. And also we have provided a Gmail ID for if you have any problem or issues after the workshop, you can contact us. We are going to start our first session in 5 minutes. So please be connected. I also request all the participants to please be muted when the speaker is giving his talk. We will give extra question answer time for you to have a conversation with the speaker and resolve all your doubts. So when the speaker is speaking, please do not unmute your mic. It will create noise or disturbance to the speaker. So it is a kind request, when the speaker is speaking, please be muted.
Okay.
Our speakers for the first session, Professor P. Muthukumar and Professor Nicholas Calvet, are with us. We welcome you, sir. And now we will start with our first session of the day. So the chairman for the first session is Professor R.P. Saini, and the rapporteur is Dr. Charmala Suresh. I will give you a brief bio of the chairman. Professor R.P. Saini is a professor in the Department of Hydro and Renewable Energy, IIT Roorkee, and MNRE chairperson. He has more than 35 years of experience in teaching and research. He is actively working in small hydropower, solar energy, and integration of renewable energy resources. There are 31 PhD awarded under his supervision and more than 300 research papers in international and national conferences. Professor Saini has 2 patents on micro hydro turbines and also received several awards for his contribution in the area of renewable energy. And the rapporteur of the session, Dr. Charmala Suresh, has received his PhD from IIT Roorkee and post-graduation from NIT Calicut. Dr. Suresh has published 5 research papers in reputed international journals and also reviewer of 2 international journals. His research area are focused on solar thermal energy storage systems, PCM, applications on thermal energy systems and buildings. Now the session is handed over to the chairman.
Thank you very much, Siddhita, for introducing us. And at the outset, I welcome to our eminent speakers for this session, Professor Muthukumar and Professor Nicholas. So welcome you, sir. And the first speaker, Professor P. Muthukumar, I think he is very well-known researchers in the area of solar thermal energy. So Professor Muthukumar is professor in the Department of Mechanical Engineering, IIT Guwahati. Professor Muthukumar has been awarded by several prestigious awards and includes Abdul Kalam Technology Innovations National Award 2020-21 from Indian National Academy of Engineers and BIRAC Innovations Challenges Awards SOCH 2020-21 from Department of Biotechnology, Government of India. Is the most recent. Professor Muthukumar has also secured a position in the world's top 2% scientists in 2020, published by Stepnor University, USA 2020. He has published more than 100 journal articles, 3 books, 140 conference proceedings. His research area is related to refrigeration, thermal energy storage, hydrogen energy, which includes storage and applications, metal hybrid based thermal machines, sorption, heat and cooling systems, and porous medium combustions. He is very active in this area. So welcome, Professor Muthukumar. And I think this session basically we put this 1 hour 15 minutes. So I request that your presentation may be in 1 hour and 10 to 15 minutes for the interaction with the participants. So welcome you, and I think now you can please share your PPT and start. Thank you very much.
Yeah, thank you, Professor Saini. And it's a pleasure for me to be here. And yeah, so and good morning, Professor Nicholas. Good morning. Yeah, and nice to see you here. Yeah, so of course, our collaboration with Professor Saini started in early 2010, and since then we are associated, in several forums, and including, of course, we also had one joint research project based on thermal energy storage system. So in this particular, talk, I try to summarize the various activities, research activities carried out here at IIT Guwahati related to thermal energy storage system. But certainly I cannot cover everything because of the limitation of time. Anyway, I'll try to throw some light towards this field for the benefit of the young researchers present here. So let me share my screen. Yeah, it's visible now, screen?
Yes, visible.
Yeah. So the topic, of course, what I have chosen here is the high temperature thermal and isotope system and concept and developmental status. This is mainly pertaining to solar thermal power plant, other high temperature process, you can say the industry. Before begin my presentation, I wanted to give you a brief introduction about our institute for the benefit of audience. So we IIT Guwahati located, in the gateway of northeastern parts of India, that is Guwahati. So whichever the northeastern state you wanted to visit, whether it's Arunachal Pradesh or Nagaland or Manipur, Mizoram or Tripura, Meghalaya, whichever the state, we have to go via Guwahati. So that's why it is called as gateway of northeastern part of India. So we established, started in 1995 and well established during 2005. We falls under the category of Tier 1 IITs. And so this is beautiful among all IITs. And I'm proud to say that we are second cleanest campus in India. We located on the river bank of Brahmaputra. The Brahmaputra has several names. And our campus is about 700 acre in size. And currently we have about 7,200 strength and about 500 odd faculty and 500 support staffs. And in addition to human habitation, we also have several thousands of migratory birds, wildcats, and jackals, and etc. This is a completely eco-friendly campus. And now you can see here, besides the campus, so it's a river. So this is the river, and these are what you are seeing our academic complex. So you can the other view. So during rainy season, without getting wet, you can reach any part of the campus. That's how it is designed. And this is the hostel areas and playground and all these things. It's a kind of always it's a greeny campus. Yeah. So now we'll go to the main topic. So the energy. So here you can see the status of renewable and non-renewable energy. Renewable and conventional energy. So if you see in terms of the source, the renewables are, as they were infinite source. Particularly if you see the solar energy, even if you consider maybe roughly about 6 to 7% conversion efficiency, and the potential of solar is huge, which is almost like 23,000 times the energy requirement of our globe. So currently, by 2000, our current need is roughly about 20, terawatt year, and maybe in 2050, this figure may go up to about 28 terawatt. This one, but you can see the potential of the solar, which is almost, very huge, and so nearly almost 1,000 times higher than our present energy requirement. Similarly, the other sources, wind and biomass, hydro, etc., these all are also having enough potential. But coming to the finite sources like the coal and petroleum, natural gas, and by nature they were limited in source. Particularly petroleum, now you are trying to extract the conventional oil, and still 80% of oil in the form of non-conventional oil is left out in the ground. If you want to extract the non-conventional oil, the amount of the energy or this one spent for extracting the remaining 85% of non-conventional oil will be very expensive, which is tedious process. Then obviously this process is going to be very expensive. Then coal, of course, we have enough resource, but again there is a environmental, other ecological issues related to coal. But anyway, I don't want to comment about those issues. But what I'm trying to say here is, the potential of solar, which is huge in abundance. But the only thing is we need to see the reliability of such sources. So coming to the solar energy, as you know, the solar is intermittent in nature, and so you won't harvest the solar energy during, you can say, rainy season or a cloudy season, which is difficult. So if you want to make it reliable, and so you need to have some kind of a temporary reservoir which can store the energy harvested from the solar during peak hours and dissipate the same during the the cloudy season or absent season. So that's where the thermal energy storage system will come into the picture. So now you can see here a typical, the solar thermal power plant, which is integrated with thermal energy storage system. So there are of course the solar fields and solar fields. The thermal energy storage system is connected in parallel with the solar fields. So particularly during say between 12 to maybe 3 p.m. and the energy harvested from the solar field will be very high. It will be 20 to 30 times higher than the designed capacity. So this excess energy can be stored in the thermal energy storage system. It can be either in the form of sensible heat or latent heat or thermochemical heat. This type of storage, varies, depends on the, you can say, the operating condition and then the, the length of storage period. Then later and during maybe option hours, like after 5 p.m., then you pass the, you can say, the low temperature, the high pressure water through the thermal energy storage system and extract the heat and convert the high pressure water into steam, and then the steam can be, of course, driven by the, the turbine. Then you will get the electricity generator. Okay. So now, if you see the thermal energy storage system, so heat can be stored in 3 forms, as I already mentioned. Sensible heat. In the sensible heat, by raising the temperature of the medium, you can store the heat in the form of sensible. And latent heat, here we can make use of the phase change enthalpy of the certain material, and so you can store the heat. And here heat can be stored partially in the form of sensible heat, maybe about 15 to 20% of heat still stored in the form of latent heat, and the remaining majority, like about 80%, will be stored in the form of latent heat of phase change. Then thermochemical, yes, this field is now it's growing up. So there are certain gas and solid, this one. When gas is exposed to solid, and then both of them will undergo certain chemical reaction. You can say the exothermic reaction. Then heat will be evolved. This heat can be used for useful purpose. For example, generation of steam. Then whenever you have excess energy, you supply the gas, heat to the system. Then what happened? The gas which is stored in the solid will be, will come out. And so here the reaction is endothermic reaction. So endothermic, you can say chemical reaction. So the gas and solid will be again separated. Okay. So this process continues. So that is the thermochemical energy storage system. Now we will see this. First, we'll see all the storage system and some of the materials. Then after that, we'll go into the research topic what we have done here at IIT Guwahati. Okay, so this is again typically the this one, the thermal storage system. So basically the thermal storage system help us in utilizing the energy harvested during the peak hours to the non-peak hours. So otherwise, if you are not utilizing this heat which is harvested during the peak solar radiation time, it is going to be waste only. So you can utilize that heat and transfer to the the early day of the the operation, or maybe in the after sunset. So in that way, you can of course you can reduce the peak load requirement, or maybe this one. So this thermal energy storage system, of course, it serves in several ways. I mean, provides a lot of benefit. It brings down the so-called the levelized cost, particularly in the solar thermal power plant. It brings down the cost. If you consider the without storage, the cost of electricity generation from the solar thermal will be approximately about 10 to 12 rupees. But if the moment you consider the storage, then the cost will come down close to about 4 to 5 rupees, which is almost in comparison with the, this price is comparison with the coal-fired thermal power plant. I mean, at the actual rate. But it also increases the reliability of the system and improve the capacity without having the additional, major components. There are several ways, the thermal energy system can be, helpful for the solar thermal power plant. And particularly in the process industry, of course, it reduces the fuel consumption cost also to a larger extent. Yeah, so in charging, typically now you consider here it's a simple storage system. During charging, what we are doing, we supply the hot fluid maybe at about 300 to 500 degrees Celsius. Then the hot fluid exchange heat with the storage medium and loses its heats and become cold fluid at the end. This is during charging and discharging. It is opposite way. You have to supply the cold fluid maybe at about 350 degrees Celsius. And then here usually the storage medium will be at a high temperature, say about 400-500 degrees Celsius. Then here heat will be transferred from the storage system to the fluid. Okay, then obviously then the fluid will come out at high temperature. So the temperature rise between the inlet and outlet of the fluid during charging and during discharging, and then the temperature drop, between inlet and outlet during charging can be, of course, fixed based on the design requirement. So everything is, you can fix your own delta T. So coming to the central heat storage system, as I already mentioned here, the heat is stored in the form of rising the temperature. So basically, the material which meant for central heat storage system should have high, the so-called the specific capacity, which is nothing but the, the specific heat, and then you can say the density, which should be high, and also the material should have the good thermal stability. It is very important. Like for example, concrete, it's a low cost and good material, but the problem with the concrete is when it is subjected to repeated cycling and thermal cycling, it will break down maybe after few cycles, and they can see the formation of crack inside the concrete block. So therefore, that will hinder the the further storage characteristics, heat storage characteristics. So the physical stability is very important. Physical and thermal stability is very important. And also the material should have good thermal conductivity for having rapid charging and discharging. So we will see some materials. So here in central heat storage, you can, of course, for storing the heat in the form of central heat, you can use liquid as well as the solid material. The commonly used liquid material, materials are like the mineral oil, synthetic oil, nitrate salt, and nitrite and nitrate and carbonate salts. Basically, in the existing solar thermal power plant located in Spain and some other European countries, they use the solar salt, which consists of about almost equivalent percentage of sodium nitrate and potassium nitrate, and they use it in the form of liquid central heat storage range. Carbonates are, it's mainly meant for high temperature of maybe up to above 800 to 900 degrees Celsius. And so remaining synthetic oils is relatively meant for the low temperature around up to about 300 degrees Celsius. Yeah, now you can see here. I think somebody is talking. Professor Saini?
We have muted. Please carry on. Please continue. We have all muted. Hello. Professor Muthukumar, you please continue. You are muted, I think.
Yeah. Okay, automatically it's muted. Yeah, yeah. Okay, fine. So the molten salt, of course, here you can see the variety of the salt which is used for sensible heat, like liquid-based sensible heat storage system. And now the people are working on the chloride-based salts like magnesium chloride, lithium chloride, and fluorides. These can provide the temperature in the range of about 800 to about 1,200 degrees Celsius. Now the researchers are looking for the high temperature, the latent heat storage system. Maybe at the end of the talk, I will present one current scenario in US, and so therefore the chloride and fluoride, these salts are being exposed. Though the fluoride-based salts are having some environmental issue, but still, people are going ahead because these salts are having the high heat capacity as well as they can be operated up to about 800 to 1,000 degrees Celsius. Yeah, many such configurations are coming up now. They can be electric salt or trinary salts. Many such components are coming. So as per the solid sensible heat storage system is concerned, and we have many material like the magnesia silica bricks, and then cast iron, cast steel, and reinforced concrete. So concrete, of course, you can go for with the suitable additives, and you can make use of the concrete up to about 300 to about 500 degrees Celsius. And even we have done quite a lot of experiment with the concrete, and we didn't face any kind of thermal cracking issue. But only thing is, when you are choosing the concrete composition, then you need to be very careful. And the magnesium-based bricks are again, it's an interesting material if you are looking for temperature above 1000 degrees Celsius. But there are issues, which need to be, discussed. Mainly, its density is relatively low compared to cast iron and other this one. That can be, of course, obviously, can improve it. So now the latent heat storage material, we have plenty of material here. So if you look into the latent heat, of course, there are three types of phase change. There is a solid to solid. Here, the enthalpy associated with this phase change is very less, so therefore, which do not have much scope in the thermal storage application. Then coming to the solid to liquid, here the enthalpy change is moderate. And so we prefer this particular phase change because the volume change associated with the solid to liquid is relatively less. In case of PCM, it will be less than 5%. So we prefer this particular phase transition for storing the heat. And liquid to vapor, here the enthalpy associated is very high, but we deliberate phase change because the volume change is very huge. So in case of the water, if you convert 1 liter of water into steam, and the steam volume will be very huge at 1 atmospheric pressure. That is difficult. Okay, so latent heat storage material, and there are several review papers already reported in this area, and one can go through it. And I can say there are more than 1000 materials are available. 1000 PCMs are available for storing the heat in the range of about 50 to up to about 700, 800 degrees Celsius. Here, actually, these materials are tailor-made, I can say, according to your requirement and temperature range. You can tailor the material. Tailor means, for example, now you see here KNO3 KCl, here 90.5% KNO3 and 4.5% KCl. If you vary the percentage, then obviously it's the operating temperature. I mean, the melting temperature, phase change, enthalpy will vary. So you can fine tune, the composition according to your requirement. So then again you can see here again the material, this one. But basically coming to this one, the main the important characteristics, of this, this one requirement should be. So this material should have high heat of fusion, that is very important, high thermal conductivity, and it should be less corrosion because most of the PCMs are highly corrosive. If you go for the nitride or the potassium based or the carbonate based salts, they are highly corrosive in nature. So you have to go for the nickel coated stainless steel, or maybe the high resistant steel, high corrosive resistance steel, we have to go for it. So obviously this will increase the cost of the heat exchanger. But we have no other option. We have to go for it. Otherwise, this it will sooner maybe the PCM will eat away the heat exchanger material. So coming to the thermochemical storage system, as I already mentioned, so the typical, the example will be the metal hydride hydrogen. I will explain you in the next slide. So the metal hydride is basically it's a kind of a solid media. It's an alloy basically, and hydrogen is a gas. When hydrogen try to interact with the the metal alloy, what will happen? So the hydrogen will be absorbed by the metal alloy, and during this process absorption, there is a chemical reaction and followed by the evaluation of the heat. So basically it's an exothermic reaction. So for example, if you take maybe 1 kg of this material hydrogen gas, which is absorbed by this one, the amount of heat released from the system will be very huge. It will be almost 20 to 30 times higher than your conventional PCM based one. Okay, it will be very huge. So therefore, this particular topic it's becoming very interesting now. Many researchers are started working on this area. Anyway, we will have details in the upcoming slides. So in addition to metal hydrides, the materials like ammonia, even the calcium hydroxide or calcium carbonate, these are the materials again. Like in the case of you take the calcium chloride and the CO2 gas or the calcium CO2 gas, and then you try to react, and of course you will get the heat will be evolved, and you will have plenty of this one. Now you see here in case of the metal hydride, the amount of heat stored per meter cube volume will be about roughly about 4 gigajoules, and which is almost, in case of the calcium carbonate also relatively high. But there are issues associated with the calcium carbonate. That of course I will. That's why. But still, people are working on it. But metal hydride can be operated here. I've given some reference temperature up to 300, but it can be operated up to about 700 degrees Celsius. So yeah, coming to the metal hydride, basically metal hydrides are the intermetallic compounds, and basically they can be produced by alloying of various rare earth metals such as lanthanum, titanium, zirconium, and manganese, and etc. They can be formed either by melting or ball milling route. Okay, so when this intermetallic compound exposed to hydrogen at certain pressure and temperature, the hydrogen will be absorbed by the metal hydride. So basically the hydrogen will be in the form of molecules, and when it is exposed to the metallic surface, the hydrogen will break into the atoms. These atoms will slowly penetrate into the interstitial position between the metallic atoms, and then later it will try to occupy the interstitial position between the two metal atoms, and by making a physicochemical bond. So during this process, a huge amount of heat will be released. For example, if 1 mole of hydrogen is absorbed by the magnesium-based alloy, the amount of heat released will be about 75, kilojoule. It's very huge. And then in the reverse, when you supply the heat to the metal hydride, and then the metal hydride, the hydrogen atom which was of course which occupied between the two interstitial position will come out by breaking the bond, and then once it comes out, then the two hydrogen atoms will join together and they'll make the molecules. So you will get back all the hydrogen. So basically the absorption of hydrogen by the metal hydride alloy, and the desorption of hydrogen from the metal hydride alloy, both are reversible in nature. And so by using these two chemical reaction, of course you can store the heat. You can store the heat for any period of time. So here just I wanted to make a point here. So once once the hydrogen is separated from the metal hydride, you can keep the metal hydride at atmospheric temperature. This is called the heat storage mode. Okay, so whenever you need the heat, and you can supply the hydrogen to the metal hydride takes the hydrogen and it liberates the heat. So this is the discharging mode. So here in case of the metal hydride alloy, you don't need any thermal insulation, and here heat can be stored any period of time, and even you can store the heat for 1,000 years or 2,000 years, any amount of time you can store it. Nothing will happen, because only thing is the metal hydride should be stored in a airtight container. That's all. Whenever you need heat, just you supply the hydrogen inside the system, then you will get the heat output. So in addition to this thermal storage, this material can be used for multiple engineering application, including hydrogen storage. Hydrogen storage is the prime application. Then the refrigerator, thermal storage, even tea freezing application, heat transformer, many application is possible. For more details, you can go through our research publication. You can find the details. So yeah, technically here in this kind of storage module, and there will be a gas bottle, the hydrogen storage bottle. Whenever you need the hydrogen, heat output, then you open the valve, hydrogen valve, then allow the hydrogen to flow through the reactor. Then it will absorb the hydrogen and releases the heat. Okay, this is, you can say, the discharging mode. Then during the charging mode, whenever you have the heat availability, then you supply the heat to the metal hydride reactor, then the hydrogen will be dissolved, and the dissolved hydrogen will be stored back to the supply cylinder again. Okay, so this is like a simple charging and discharging. Here the storage capacity, if you take 1 kg of hydride, you can store about 2.2 megajoules of heat, which is almost equivalent to the latent heat of this one, the phase water. And here as I told you, no thermal insulation, and heat can be stored for a longer period of time, and regeneration will be easy, and you can get the exergy efficiency very high, as close to maybe about 60-70% you will get. So yeah, these are the metal hydrides, the few class of metal hydride and their respective operating temperature. And so if you consider the titanium and lanthanum based hydrides, these are a bit expensive, but they can be operated up to about 700 degrees Celsius. So these material can be used for simultaneous, storing the energy as well as the producing the cooling also. That I will tell you how this can serve. Yeah, again some more basic information here. So here, like for example, when you are observing the hydrogen, so if you supply the hydrogen at high pressure, say about, you see this particular alloy, pure magnesium, and if you supply the hydrogen maybe at about 50 bar pressure, then you can get the heat output in the range of about 460 degrees Celsius. Okay, 460 degrees Celsius. So by manipulating the pressure, supply pressure range, and you can increase, you can get the heat output at higher in a temperature as well. Yeah, again, whereas when you can see here, this is the working temperature range magnesium. These are the kind of complex hydrides, but these hydrides are in the still it is in the R&D stage, and there are issues associated with these hydrides, mainly the cyclic stability. But people are working on it, and most likely they will get some breakthrough. But what I'm trying to say here, these materials are having very high inner storage density, very high storage density compared to the other, the hydrides. So typically, you see here the metal hydride based thermal storage system. So whenever you have heat, excess heat available, and you can supply them to the high temperature alloy. High temperature alloy means this is a magnesium based alloy. Then you dissolve the hydrogen to the low temperature alloy. Okay, through a regenerator, you store it in the low temperature alloy. So let us assume you are dissolving hydrogen from the high temperature alloy, maybe at about 5 bar pressure. Okay, I'm giving an example, 5 bar pressure. The corresponding dissorption temperature may be around, say, 350 degrees Celsius. Then you are allowing the hydrogen to absorb at low temperature alloy around room temperature. So at maybe 35 degrees Celsius, you observe the hydrogen at 5 bar. So here this heat can be rejected to the ambient. That is, the ambient can be treated as a heat sink. Okay. So this is your charging mode. Okay, you are charging the hydride in the system. So whenever you need the heat, say during night time, now what you can do with the help of a small compressor, you can have one small compressor and try to dissolve the hydrogen from the this low temperature alloy. Now what you can do, you try to dissolve the hydrogen from the low temperature alloy maybe at about 1 bar pressure. Okay, and deliberately I'm going for low pressure. So when you reduce the low dissorption pressure of the low temperature alloy, automatically temperature will reduce. Okay, that the dissorption temperature will reduce. Now here, if you dissolve the hydrogen at say about 1 bar pressure from low temperature alloy, then the low temperature alloy can produce the cooling effect maybe around 10 to 15 degrees Celsius. Okay. So this cooling effect will be almost equivalent to the amount of heat which you have supplied to the the high temperature alloy. Almost the same. Maybe it may not be the same, but slightly less. But you will be getting huge amount of cooling effect at about 10 to 15 degrees. Then since we are having a compressor here, then you boost up the hydrogen pressure, say from 1 atmospheric pressure, maybe you to about say 25 bar. Okay, I'm giving an example. Then you pass through the regenerator, because when you are dissolving the hydrogen will be dissolved at 350 degrees Celsius. The heat carried away by the hydrogen gas will be stored in the regenerator. Okay, but it may be less quantity, but still you can make use of it. And then after compression, then during the reverse cycle, I mean the discharging cycle, then you pass the pressurized hydrogen at about 25 bar through the regenerator, so it will get some heated up. Then you supply to the high temperature alloy. Now what is happening in the high temperature alloy? You are supplying hydrogen at high pressure, about 25 bar. Now if you see the corresponding equilibrium temperature of the high temperature alloy at about 25 bar will be around 450 degrees Celsius. Okay, so that means you will be getting heat output at 450 degrees Celsius. Now what is happening in the system? You are supplying heat to the metal hydride system during the charging at about 350 degrees Celsius. During discharging, you are getting two outputs. One output is from the low temperature alloy, you are getting the cooling at about 10 to 15 degrees Celsius. In addition to this cooling, and you will be getting the upgraded heat output at about 450 degrees Celsius. Okay. So this is this is the the heat transformer. You can say the poly generation system. That means for a single input, you are getting the multiple output. So this kind of process possible only with metal hydride. You cannot have this kind of upgraded output and heat output with cooling, simultaneous cooling. This you cannot get it from any of these systems. Anyway, so now currently we are investigating it. We have done thermodynamic studies. One of my students is building the experimental setup, and hopefully in about 3 to 4 months time, we should be in a position to produce some, good results. Okay, so what we have seen the three basic, category of, the thermal storage system. Now we'll see the storage concept. Heat can be stored in the form of active storage and passive storage and hybrid storage. In active storage, again, we have the direct and indirect. In the direct, both the thermal storage media and the heat transfer fluid will be the same. Okay, that is the direct active storage. In case of the indirect, the thermal storage media will be different from the heat transfer fluid, that is the indirect. Here we have the two-tank system, thermocline system. And passive storage, here the heat transfer media, the thermal storage media will be transit, like the concrete and ceramic and PCM, these are the one. They will be, in stationary, of course, they won't move. In case of the active type, the heat transfer fluid, direct active type, the heat transfer fluid itself will act as in a storage media. That means the heat and the storage media itself will be in movement. Okay. In passive, it will be stationary, and hybrid is a combination of both active and passive. Okay, coming to the the design record, design criteria. So the basically the storage capacity, the material should have high storage capacity and efficiency. That is the in terms of efficiency, there should be a good heat transfer characteristics between the heat exchanger and the heat transfer fluid, which is very important. And life of the storage media is concerned should be long, and particularly they should have long, very good mechanical and chemical stability. And the safety issue, I mean the heat transfer fluid or the heat storage media should not react with either with the heat transfer fluid or with the heat exchanger. Like in case of the PCM, PCM material, which are most of the PCMs are highly corrosive, so then we'll have issues. And then thermal loss should be low, and then the controlling of this one should be this one. And these are the usual technical requirements. In addition to that, the material also should have high thermal conductivity, high stability, and the cost should be reasonable. And then cost of the heat exchanger also should be reasonable. Then the the system should occupy lesser space or the enclosure. So these are some of the technical as well as the other requirement. So we will see the design procedure of the system. Let us take you can take either the sensible heat storage system or latent heat storage system. First, the design for the first design. So we need to fix the storage capacity. Say whether you want to go for what kind of capacity you want to go for. Say 100 megajoule or 1 gigajoule, depends on the requirement. So once you finalize the storage capacity, then you need to find out the volume of the material. In case of the sensible heat system, for finding the volume, we need to have the temperature difference and specific heat of the material. Once you know the specific heat and temperature difference, and then you can find out the the storage capacity. So Q is equal to mCp delta T. Then the mass can be found out. And in case of the latent heat storage system, and once you identify the material, you can get the latent heat. Once you know the latent heat, then you can find out the mass. Okay. So now here, once you find out the mass and volume can be found out based on the density value. And once you know the volume, and so the first strategy here is that you can fix the length of the storage module, because this usually for the industry. They will finalize the length. This is mainly to minimize the pressure drop. You cannot have the infinite length of the heat exchanger, otherwise you will end up with having huge pressure drop. So considering the pressure drop of the heat transfer fluid, you can fix the length. So once you fix the length and volume, then the heat exchanger, kind of the number of tubes through which the heat transfer fluid will be supplied can be identified. Based on the the optimum, you can say the charging and the discharging time. So for finding the optimum number of charging tube, what you have to do, you have to do the thermal modeling. Through the thermal modeling only we can help. So now just to see here, it's a concrete based sensible heat storage system. Here you can see there are about 9 this, and we have taken some number of tubes, and each number of tubes is having these external fins. Maybe about six fins are having 6 fins, and the height of the fins and the thickness of the fins, everything need to be fixed. And here also the number of tubes also need to be optimized in such a way that then there should be enough volume for storing the required material. So here, of course, the you can do the modeling by using any one of the standard, the package. So usually we use the COMSOL multiphysics software, which is again user-friendly one. So here model can be done separately for the heat transfer fluid as well as the storage media. The storage media, the heat transfer mechanism is only conduction. In case of the heat transfer fluid, you will have both the convection and conduction. Then at the at the surface, at the fin surface, I mean at the tube surface, you can apply the the convective boundary condition. Then you can do it. So the initial and boundary condition that you can set based on the charging and discharging process. And then here the input value can be the fluid velocity and then temperature of the fluid. All these things can be specified. Then you can solve the system. And here what we got done, so we varied the number of charging tubes, keeping the symmetry of the system as this one. Symmetry means, and if you take a diagonal line and in both the sides should have the equal number of tubes. So by keeping the symmetry, we varied the number of tubes. Then and accordingly we have predicted the charging time. Just this is one example. So now if you see here, if you increase the number of tubes and the charging time, of course, found to decrease significantly. But here you can see here there are between 19 to 21 tubes. The slope of this curve is very low, and another region where it down 21 to 29 tubes. Here also the slope is less. So that means here you can have the optimum either in between 27 to 29 or between 19 to 20. Okay, 21 tubes. So for example, if you choose the number of tubes between 27 to 29, the volume left out for storing the heat transfer material or the heat storage material will be very low. That means the tube itself will occupy more amount of volume. So then obviously you cannot get the desired capacity of say about 50 megajoule or 100 megajoule, whatever it may be. So therefore, the higher number of tubes is ruled out. And then if you choose the between 19 to 21 in this range, though here we are sacrificing little bit of charging time, higher charging time, but still, at this range, the available volume for storing the, this material will be, good enough. So therefore, you can choose the number of charging tube as, 19. The 19 in the at center there will be tube, and the first row there will be about 6 tubes, and then the second, you can say the each circle diameter this one you will have 12 tubes. So in that way you can optimize. So yeah, we developed the the test facilities for testing the thermal storage performance of the various system. So it's a huge setup, and the heater is about 85 kilowatt heater capacity, and then the storage tank about 3,000 liter storage tank, and which has the expansion tank and cooling tank and all these things. And there is a pressure pump, and then the flow control valve. And with this setup, of course, yeah, we have the turbine type flow mass flow meter also for this one. Then the storage module can be connected here, and so we have all the safety and the bypassing circuit for this one, and you can see the photograph. And yeah, this is the storage module. What you can see here, this the storage oil tank, which is about I think 3,000 liter capacity. And top you can see here this expansion tank, and this is the cooling tank. Here we have the thermic plate heater of about 85 kilowatt capacity, and there's a pump. Okay, so with this setup, and you can perform the experiment. You can test any storage media. I mean, maybe a sensible or latent or thermochemical. Thermochemical we have to start, but latent and sensible heat we have done it up to about, with this oil, thermic plate oil, we tested up to about 350 degrees Celsius. For high temperature, we have the another setup. This is the storage module, what you can see here, and they all are connected with thermocouple and everything. Yeah, so we tested here the concrete based one, cast iron based and cast steel based, several devices we have tested. And this is the concrete based one, and here we have the copper tubes as well as the stainless steel tubes and finned tubes. And so these are the header, and through which the fluid will be supplied. Then from the header, the fluid will be equally distributed to all the tubes through the tubes. Then at the end it will come out. And here there are the PCM based one. Here in the PCM, actually there are 3 compartments. We made it, and each compartment, in each compartment, different PCM can be filled, so that you can have the cascading effect. So this is the cast steel. Cast steel basically, we bought a huge block of cast steel where the through holes are made here, and through which the fluid will be supplied. I mean, the fluid will be supplied. To measure the temperature history, we have the different thermocouple, inserted at different radial as well as the axial distance. So they can be used for validating our thermal model. And here you can see here the PCM. There are 3 compartments. In each compartment, a different PCM can be filled. So when you are filling it, and you have to melt the PCM, and then after that in the form of liquid you have to pour it inside. Okay, so we have to be very, very careful. Here what we are taking 12% NO3 and 44% CNO3, and then remaining about 38% will be the the potassium nitrate. So yeah, this is the thermocouple position, and these are tubes and thermocouple position. So we have the thermocouple at different axial location and different radial location also. So this can be used, these temperature data can be used to analyze the movement of the PCM during the melting. So we have done the detailed characterization. Here just we have taken the 2 component salt like sodium nitrate and potassium nitrate, and their composition can be varied. And see here the melt fraction and the respective, these are the composition and the melt fraction, and this latent heat also. So then finally, the melting temperature can be expressed as a function of composition. Okay, the percentage of composition, and similarly enthalpy also can be expressed. This is just an example we have taken, and similarly you can also do the similar studies for the other 2 salt or 3 salt system also. So what I am trying to say here, so if you want a particular temperature as a melting point, then you can find the value of Xi here. Okay. So it is in a system it's a tailor made, and you can have your own PCM according to your requirement. Everything is possible. So here you can see here the typical this charging this one. I mean charging the system. It's a melting phenomena. Here the local temperature versus the time, and so the flat line shows the melting of the PCM because the melting will be near uniform temperature. So basically here from the we are supplying the fluid from left to right, and the red one shows the this is the the left one the left portion, and the middle one is the middle one. This one, the last green line is the last one. Okay, and there are 3 thermocouple, the top and middle, and this is the bottom. Now you can see here the temperature. There is a large, even if you take one particular section, there is a large temperature gradient between the top of the PCM, top of the container, and the bottom of the container. That shows the the movement of the fluid and the convection effect also. So everything can be captured with the temperature data. And similarly, the solidification, of course, you don't see much temperature gradient, because when it started, in solidification it's a pure conduction, whereas in case of the melting, it is a combination of both conduction and convection. Yeah, so now let us move to the concrete-based one. In the concrete-based one, we have done a lot of studies, and before choosing the concrete composition, we developed several such these concrete modules, and based on the standards like the M5, M10, M15, M30, and etc. And based on this ISI standard, we have developed them. And all these blocks are, of course, went through the successive compressive and tensile stress, and then we found out the respective strength also. Then the required composition for our thermal storage application is selected, based on the high strength versus the cost. Okay, cost. I mean the strength versus the manufacturing cost of the concrete block should be high. So based on that, we have chosen this one. Yeah. So then based on that, we have taken the M30 configuration for this one. This is the the Fibor casting. This is where you can see the auto casting. So we have developed such models, and then we tested all the performance. So the later, of course, we found that the thermal conductivity of the PCMs are very low. So we are trying to adopt several heat transfer enhancement techniques, and we went through, we explored several techniques as well. Some of the techniques are very simple, but result what we got is very significant. I'm going to highlight you some of the techniques. So this is the basic encapsulation. Here the diameter of this capsule is about 63.5 mm. Salt, what we have taken is sodium nitrate. Okay, the amount of heat stored is about 0.5 megajoule, and this is our proposed novel encapsulation capsule. Here, what we have done, we we inserted a quarter-inch tube here, quarter-inch tube. For in both the cases, we fill the same amount of material. Since we inserted one small tube here, so slightly this diameter increased, maybe roughly about not even 1 mm, less than 1 mm increase. So with this arrangement, and you can see here, we can reduce the the charging time by about 30%. In case of the discharging time, you can reduce nearly even more than higher, about 40 to 50% you can reduce. So by providing a hole at the center, this will reduces the effective thermal resistance of the system. Therefore we could get the rapid charging and discharging. Yeah, you see here, even in case of the melting and the discharging, in fact, rather it is very fast compared to this one. And charging time, we could reduce about 44%, whereas the discharging time we could reduce by about 70%. Yeah, again, this is for the high capacity one. For a different temperature range, also we have done it. And again, for all the cases, we got better results compared to this one. Again, even for the higher storage capacity also. And I have the next slide. So here, what we got done here. Yeah, this is very interesting figure. These are the basic capsules like 0.5 megajoule, 1 megajoule, 1.5 megajoule. And here we have the novel capsules, again 0.5, 1 and this one. Now, if you see this one, the novel capsule of having high capacity about 1.5 megajoules performs almost similar to the basic capsule of having 0.5 in this one. So that means even if you increase the size of the novel capsule by 3 times, and its performance, its charging and discharging is almost similar to the capsule, which is a basic capsule, which is having 3 times lesser in dimension. That's what I'm trying to say. So in that way, you can reduce this, size as well as the, space requirement also. Now you see here, this top one, this is the, your basic capsules. Okay, so in case of the basic capsule here, we have nearly about 38, tubes. And this 38 tubes can be replaced with about 19 tubes. 19 tubes and of having the novel capsules. So in that way, you can reduce the so-called the material requirement by about nearly about 60% you can reduce. And this is again for the circular configuration. Here we have for the rectangular configuration. So in that way, the manufacturing cost, by adopting a simple strategy, you can reduce the manufacturing cost by nearly about 50%. Yeah, and again the fins also. This is the normal the tubes without any fins. This is a heat transfer plate, and in between the heat transfer plate and the outer the jacket, the PCM is filled. And this is a simple tube. And here we have a standard fin. Standard fin is basically it's a rectangular fin. There are about 4 fins. And the latter case we have the novel fin. Novel fin means you can say the taper fin. So here what you can do, you take one pin and diagonally cut, and you will get 2 parts, and each part you can fill it. So that means technically you can reduce the the pin material by about 50% here. So with this arrangement, and see here, the novel fins are performing better than this you can say the normal standard fin. So actually in the standard fin, here when the fluid is entering here, the fluid will have the temperature difference between the fluid and the storage material will be very high. So therefore, you don't need more heat transfer area here, because of the temperature difference potential itself will take care of the heat transfer rate. But when the heat transfer plate approaches at the rear end of the the module, what happens? The heat transfer plate loses its temperature. As a result, the delta T between the heat transfer plate and the storage material will be low. This low delta T imposes the heat transfer rate. So therefore, to enhance the heat transfer rate at the exist of the the storage material, we need to find some way for augmenting it. The one way is to increase the fin surface. So by deliberately increasing fin surface at the exit, then you can get the better heat transfer rate. At the same time, you can reduce the fin material by about 50%. Yeah. So this is the one, and here also with novel fin, charging time is reduced about by 13%, and discharging by reduced about 6%. So this is the another this setup. It's basically it's a air setup. Here with this setup, we have 48 kilowatt heater and the flow air of about 120 meter cube per hour. So here the temperature can be operated up to about 600 degrees Celsius using air as a design. Yes, please. No, I'm in a talk. You meet me after 2 hours. Yeah, so so we have all these flow measuring device, sensors, pressure sensors, temperature sensors, etc. So here you can vary the airflow rate and the temperature, everything can be varied. We have done a lot of experiments here, and most of our papers are available in applied energy, energy conversion management, and solar energy. You can see our publication. Yeah. So this is this is a concrete based one. Here also we have tested, and it's a simple kind of a module. And with this module, we have we made this a kind of a sensibility storage module. Here we made several cartridges, and all the cartridges can be kept inside this module, and they can be tested. Maybe in a single go you can do the multiple experiments. So here what we again, this is the the basic capsule and the capsule with the novel capsule at the center. What exactly I have shown you earlier. So that also we got tested. Then again with the different configuration also we got tested. This is the basic capsule without any kind of this one. And this is the annular capsule. That is the capsule with the center tube. That is we can say the novel capsule. Then we went for the fin, the same capsule with the fins. That is with longitudinal fin, 4 numbers of longitudinal fin. That is the fins are in the uniform size. And fourth one is decreasing taper fins. That is the here at the inlet the more fin will be there, and outlet this is the less fin height. Then fifth one is its opposite. Okay, so this kind of configuration, of course, we have tested and experimentally and with various operating conditions. Okay, now you can see here this is the experimental this one for the cast steel and the cast concrete and cast iron. We have tested several material, and some of the one this is for the charging. This the the temperature of the inlet temperature, and this is the delta T between the inlet fluid inlet and outlet. And then the what you can see here, this is the brown color and green color. These are the temperature of the storage module, and below you can see here the amount of heat stored in the storage module. Anyway, I cannot go into the details because of the limitation of the time. I wanted to cover more information. Okay, just I am giving you a glimpse of about our work. All these works are published, and of course you can go through it in our publication for the details. Yeah, so the the latent heat storage system, again there are a lot of here. We went up to about 380 degrees Celsius. It's the inlet. Then the storage module will be about the initially it is 275. Then we are charging at 375 degrees Celsius. Then flow rates, different flow rates, everything we have done it. So what I'm showing here again, these are the for the this material. I will skip here. Yeah. So what you can see here, the interesting earlier I have shown you 5 configuration. This configuration. This is very interesting. This configuration, all these 5 configuration we have tested, and that's what you are going to see these results. So in among all the configuration, there is the configuration 3. That is the straight fin. Having about say 100 minutes. And then the this is the taper fin. Taper fin having the thickness having higher fin height at the exit. So the this is the case 3. It's a complete fin. Okay. So there is a comparison with case 3 and case 5. You can see here. There charging times are more or less the same. But in case of the case 5, you will be having 50% this less material requirement. Okay. So in case of the discharging process, in case 3 and case 5, all are more or less same. Okay. So that means by having this kind of configuration, you can reduce the material requirement by 50% without compromising the charging and discharging rate. So like this you can do it. And another one also we have done the so-called the tapered this one system. This is the normal cell and tube kind of a configuration we have taken. And then the second thing what we have done is a taper one. Taper one means there is at the exit of the the system we kept the less material. This is because when the fluid comes out from the exit, its temperature will be low. So the low temperature difference between the fluid and the material, that will impose the restriction to the the heat transfer. So to overcome this restriction, we deliberately kept less material at the exit. Okay, by having this kind of a taper section. So here what we have done, we varied the taper angle to from 1 to about say 4 degree, and then we studied its effect, and we found that the taper angle of about 3.4 degree, of course, provided the better performance in terms of charging and discharging. So when you maintain the taper angle of about 3.4 degree, this one, and the charging and the discharging rates, of course, improved by about 17 and 28%. That means the charging time and discharging time got reduced by about 17 to 28, 17% and 28% respectively. So this is another interesting result. One can also have this kind of configuration for having the better heat transfer enhancement. And as usual, remaining things we vary the temperature, pressure, and all these things are possible. Then again, another configuration also we have done again with the taper, the cross section, and as well as the design A is a normal fin. There are 4 straight fins, and design B is the taper pin with the increasing pin thickness from inlet to outlet, and design C is the here. Decreasing pin height from inlet to outlet. Okay, but inlet here you will have the more PCM, and outlet less PCM, and similarly the height of the pin also at the outlet less. Okay, like this we had the other configuration. So here we found design C is the best. Okay. Fine. So this design C, of course, found to reduce the charging and discharging time by about 19 and 15%. Okay, this what I have discussed, the metal hydride based poly generation system. So this system, of course, provides simultaneous, the thermal storage, thermal upgradation, and cooling. Okay, all 3 things can be possible by using a single system. So we have done so far. We have done the thermodynamic study, and then recently we are initiated the testing of the high temperature thermal storage system using magnesium based hydride. And that is coupled. Soon we are going to couple with the low temperature alloy. Then we can have all the multiple this one. So here, you can see here, but this is the heat input about 6 kilowatt. Per 6 kilowatts of heat input, you can get the heat output close to about 5.6 kilowatt output. In addition to that, you will be also getting the cooling effect of about 2 kilowatt. So here the overall COP will be close to about 0.4. So huge. And then efficiency, energy. The exergy efficiency or the energy, the storage efficiency is close to about 85 to 83%. So technically here, no, insulation is required, and heat can be stored for a longer period of time. So this is the proposed experimental setup. So we have both the high temperature loop and low temperature loop, and then from the low temperature loop you can get the cooling output. The high temperature loop you can use it for storing the heat, and then upgrading the heat from say about 350 degrees Celsius to about 450 degrees Celsius. Okay, so then I'm going to highlight you one industrial, the one on-field, you can say the demonstration. So this is one of the solar thermal power plant located in Chennai near Thirukkalukuntram. There is a place called Thirukkalukuntram. One school is there, Padashala School, where we have implemented our system. So here, actually, my expertise is to design the steam accumulator, and as well as the PCM based container of about 0.25 gigajoule, and this one will be about 1.25 gigajoule. It's a huge system, and then design them and test them and integrate with the thermal power plant. That is this one. So we can see here, this is the field, and what you are seeing here, this is a huge drum. This is the steam accumulator, about 1.25 gigajoule capacity, and then besides that we have the PCM based container also. This is basically it's the Fresnel collector. So the first one is, you can see the evaporator section here. This is the evaporator section, and this is the superheated section, and the thermal storage is kept between the evaporator and the superheating section. And this is the specification of the steam accumulator, and the capacity is designed capacity was 1 gigajoule. The pressure volume, the vessel volume is about 18 meter cube. Then design pressure is about 60 bar, but tested up to about 90 bar. Yeah, hydrostatic test pressure, and everything is designed as per the Indian boiler regulation. Okay, and the charging pressure is about 45 bar. This one charging pressure is 55 bar, and discharging pressure is 45 bar, and here heat is stored about 220 degrees Celsius. Okay, this PCM actually what will happen in the steam accumulator when you start consuming the steam, the pressure will decrease as a result, and because of the flashing, and as a result, the temperature of the steam will drop down. So the main purpose of the thermal storage system is to deliver the heat at constant temperature. So when there is a decline in pressure, to compensate the loss of pressure, we need to supply the auxiliary heat. That auxiliary heat can be produced provided from the PCM. So here we selected the PCM like sodium nitrate 60%, potassium nitrate 60%, is having the melting temperature in the range of about 219 to 225 degrees Celsius. That means when the steam temperature goes below say 220 degrees Celsius, the PCM will solidify. It will provide the heat to the steam, and it will try to maintain the temperature as close to 220 degrees Celsius. Okay, this is the the steam the PCM container. Again, it's a cascade system. There are about 144 tubes which are half-inch, and then we have done the detailed this so-called DSC analysis also, and we found out the melting and melting temperature range and their respective enthalpy, and then based on that, and you can see here how they were integrated with the steam accumulator. Okay, there are several thermocouples for capturing the temperature history during the melting of the PCM, and so that's how this being insulated. And so yeah, and this is the because the charging, because we got to completely make the PCM in the form of liquid, then you charge them carefully. Then before making the system into operation, this being tested hydrostatically at about 90 bar pressure for about 48 hours. After that only this was allowed to test. And here you can see the hydrostatic pressure at the field. But in the plant also it is tested about 90 bar pressure for about several days. But in the field also we got whole components we got tested about 90 bar 70 bar pressure. And then kept it for about few days, and then after that only this was put into the action. So we have all the safety features. This one. Okay, so now I'm going to show you some of the thermal storage system in the global perspective. So the total number of solar thermal power plant, which is about 170. This is slightly, 2 or 3 years old data, but more or less the numbers are similar. And parabolic top is about 111, central tower 40, Fresnel 16, and TC 3. And the system which is coupled with the thermal storage system are about 84. Most of them are 2-tank system, and these are available in Europe and particularly in Spain, and some part of US also it is available. In India, we have a couple of them. This is in India. Total number of solar thermal power plant 12, and these are the details. And number of power plant where the storage is implemented is 4. Most of them are 2-tank system, but there are some recently some plants are coming up with the sensible grid storage system. That is the iron ore based sensible grid storage system. They are coming up, and again this is the detail about the the system. Okay, so thank you very much, and Professor Saini, maybe if you permit me, maybe for another 4 or 5 minutes, I wanted to give you a small talk about our porous radiant burner. So this is mainly for the benefit of the audience. Can I?
Yeah, yes. 3 minutes, and then remaining time we can ask the questions.
Yeah, yes. Okay,
Please.
so I have to go there. Okay. This actually porous radiant burner, I wanted to give a talk. So where usually people are excited about this technology. That's why I wanted to. Yeah. So the screen is visible.
Yes, visible. I make is a full screen.
Okay, fine now.
Yeah, it's fine.
Okay. Yeah. So this is it's all together. So, the one of the very interesting topic where government is also very keen, and I got several award and several projects based on that. Soon we are going to launch the commercial product also. That's why I wanted to share my experience. It's of current, people of industry can say everyone will be interested about it. Okay, so as you know, the our cook stoves, whatever the cook stove we have, the commercial market are having low thermal efficiency. about 60 to 65%, and besides that, we have high emission. So there are several things are associated with this, like the LPG consumption rate is increasing at a rate of about 8% every day, and government is planning to reduce the LPG import by about 10 to 15% in 2030. This is one of our goal. Another government vision is to provide 100%, provide clean fuel to 100% population by 2030 as part of the Sustainable Development Goal, where we also committed to that. And we are also trying to explore the liquid fuels such as methanol, ethanol, even hydrogen also for cooking application. That is our another plan. And we don't have any cooking device for these liquid fuels, and including biogas also we are promoting. And yet we don't have the proper solution for it. So whatever the conventional burner available in the market, this works on the pre-flame combustion, where you can see the flame on the top of the flame. So because here at the center of the flame will experience high temperature, and if you see the temperature gradient between the center and outer periphery of the flame, which is in the order of about more than 300 degrees Celsius. So this high temperature gradient promotes the formation of thermal mass. And coming to our technology, basically it's a porous radiant burner, our technology, and which consists of two layers of porous matrix. One is the preheating zone, and another is a top one is the combustion zone. The preheating zone is made up of low cost ceramic, low thermal conductivity, and low porosity. And the combustion zone, that is the top one, that is the brown color. This you can say this brown color that you can see, that is made up of high thermal conductivity, high porosity, high emissivity silicon carbide in a matrix. So here air fuel mixture is introduced through this preheating zone, and then combustion will be initiated within the matrix. Since the combustion is happening inside the highly conducting and radiating porous matrix, some part of the combustion heat will be transferred back to the preheating zone for preheating the air fuel mixture because of the volumetric heat transfer. So because any combustion happens inside the porous media, then the radiation will come into the picture. Since the radiation is a multi-dimensional phenomena, which is also travels at a speed of light, because of the preheating effect, here the combustion is 100%. And then because of the preheating effect, we can minimize the surface temperature from 1300 degrees Celsius to about 1000 degrees Celsius. This preheating, this is called the excess enthalpy combustion. This concept allows us in minimizing the temperature around 1100 degrees Celsius, and also to have combustion efficiency close to 100%. With all these multilateral benefits joins together and provides the fuel saving of about 30 to 40%, which I'm going to tell you here. And so we have developed several burner, and for various applications, you can see here the domestic cooking application of having power input about 1 to 3 kilowatt. Here we got thermal efficiency close to about 82% in comparison with the thermal efficiency of the conventional burner of having about 65%. Here we got about 30% fuel saving. And a commercial burner of about 7 kilowatt, here we got 40% fuel saving. Cluster burner of about 15 to 18 kilowatt, here we got 50% fuel saving. And then the biogas burner, here also we got about 22% fuel saving. All these burners are tested based on the standard protocols available in this one. Then similarly, we have also extended a technology for the kerosene as well as the methanol. Also we got done it. Here also we got interesting fuel saving. Anyway, so then we are also planning for other product like the cremation unit, sanitary napkin disposal unit, medical waste disposal. Several such products are lined up. Okay, so what I'm going to, anyway, I will skip it. I know the time is important. Now you can just, I'll play you a few videos. You can see here. This is the LPG cook stove for about 5 to 7 kilowatt. Now it is in operation. You don't see the flame. It's a flameless combustion. The heat flux is uniform, and then it will create the. Here we could minimize the CO NOx emission by about 80%, besides having about 35 to 40% fuel saving. And now you can see the cluster burner is used for the hotel industry. Here you can get fuel saving close to about 40%. Okay, now now you can see here it's a biogas burner. Okay. Anyway, just I wanted to give you a small glimpse about this one. Yeah, fine. So thank you. So now my talk is open for the discussion, and
thank you very much, Professor Muthukumar, for the very, I can say, the excellent presentations you covering the. I think you started from the basics of the solar thermal storage, and then to the final product, this thing, that design aspects, everything you have covered in this. So thank you very much. It has been very excellent talk about this solar thermal energy storage. And we have 3 minutes left. So I invite that 1 or 2 questions from the participants. If they, of course, we have a few queries we received in the chat box. So I think depending on the time, we will just put those questions. Otherwise, I'll communicate. I'll forward these queries to Professor Muthukumar, and then when we receive this response, then accordingly we will forward to the participants. So 1 or 2 questions from the participants, please.
Sir, I have one question.
Yeah, please.
Sir, for encapsulation of PCM, what kind of materials we can use?
Okay, yeah, fine. So it depends on,
Yeah.
yeah, it depends on the the PCM material. Hello, am I audible?
Yes, sir, audible, sir.
Yeah. It depends on the the material, PCM material, and as I already mentioned, most of the PCMs are highly corrosive in nature. If you are going for the nitride or oxide, hydroxide based salts, you have to use the nickel coated stainless steel. At least you have to go for minimum SS 304 or 304 or 302. It should be nickel coated one. And if you are going for even normal SS304 or 302, if you go for it, and then you will end up with corrosion issues. So that you have to be very, very careful. So what we went for the whatever the material you are saying. These are the since it is a demonstration level, this one we have to all these materials are SS316, which is very expensive, but everything is coated with nickel here.
Okay, I think 1 more questions we can have.
Thank you, sir.
1 more question. So I just read that there are 3 queries the participants put. One is what is the cost of solar thermal power plant per megawatt? That is in general, somebody asked.
Yeah, so we cannot, yeah, it's a very trivial, typical question to answer. It's all depends on the type of technology.
Yes.
We cannot give. We cannot give.
That's why I'm talking about this. That we cannot just. It is difficult to answer that.
Yeah, again with the storage, without storage, and type of technology and temperature range. So many parameters.
Another question is, what are the challenges associated with direct steam generations via single pass using PCM based thermal storage? Challenge.
Yeah, see, I mean, you mean to have this embedded, like in this kind of thing. We also explored like in this kind of steam accumulator. Initially, we thought of keeping the the PCM cartridge inside the steam accumulator itself. Then later on we went through several exercises, and because the moment if you go for the salt, PCM based salt, which is highly corrosive, and if there is any puncture is happened, then everything will get mixed inside the system. So there is a danger. You see, here as such the processes and technique is okay and process is okay, but the thing is your heat exchanger material, how strong your heat exchanger material, and how do you ensure there should not be any corrosion with your PCM. So if you ensure absolutely your PCM is corrosion free, then you can integrate it. There is no issue.
So there's some more the queries. So I think those we will forward to you, sir, and then we'll get the response accordingly. We will forward to the participants.
Or else the candidate also they can write to me. I will also.
Okay. Yes. Thank you very much for the wonderful and excellent things. And we also need your this presence in the next session also as a chairman, sir.
Okay. Yeah, please. Just you give me a reminder. I am in the office only. When it starts.
Yes, we will. So thank you very much for joining us. And now, Siddhita?
Yes, sir.
It's over to you.
Yes, sir. Now I would like, thank you so much, sir, for your presentation. And we request you to join at 2 p.m. for the next session as a
Okay. Okay.
chairman.
Sure.
Yes, sir.
Yeah.
Thank you,
Sure.
sir.
Sure.
And now I would like to request chairman of the session to invite our second speaker of the day, Professor Nicholas Calvert.
Good morning. Can you hear me?
Sir, yes, sir. I can hear you.
Okay. You don't want to have a break, or we start immediately?
Sir,
Hello. Can you hear me?
Yeah, we can hear you, sir, and we welcome you in this, as a second participant in this session. And so, participants, our next speaker in this session is Professor Nicholas Calvert, and he is working assistant professor at Khalifa University of Science and Technology in Abu Dhabi, UAE. Professor Calvert is the founder and chief of the Masdar Institute Solar Platform, which is the first R&D platform in the UAE dedicated to concentrated solar power. It's a CSP and thermal storage. This Professor Calvert is representing the UAE at the Solar PACS Executive Committee, a technology collaborative program from the International Energy Agency. Professor Calvert received his BSc degree in physics and MSc in solar energy from UPVD, France. He obtained his PhD in engineering science, energy and environment field in 2010 at the PROMES CNRS laboratory, France. In 2011, he joined the National Renewable Energy Laboratory, NREL, in USA, working in the CSP group. He has also worked at the CAIC Energy Corporate Research Center in Spain in the area of TES group before moving to Abu Dhabi. So I welcome you, Professor Nicholas, and you please start that again. It's about 1 hour, so your presentation, and 10 to 15 minutes question answer. So
Thank you very much for this kind introduction. So first of all, thank you for inviting me this workshop. It's a real pleasure to be here with you today. So a little bit on my background, as mentioned in the introduction, I'm French, so I'm coming from south of France, a small city. Well, let me put the laser point. So a small city in south of France, really close to the Spanish border. And I did my PhD in the PROMES CNRS laboratory, which is a laboratory who own the biggest solar furnace in the world that you can see on the top picture. It's a 1 megawatt thermal solar furnace built in the 70s by Felix Trombe, and it's still the most powerful solar furnace today, so it's remarkable. So what's the purpose of this furnace? For example, you can test material under very high flux. So for example, when a spaceship is coming back from space, the surface of the spaceship is submitted to a very high flux, and the only way to reproduce this flux is this solar furnace on Earth. Okay, so I grew up with this culture of CSP, and then I moved to US, where I continued to work on concentrated solar power. And at this time, Gema Solar, that I will introduce later, which is the first commercial tower using the two-time molten salt system, was integrated in 2011. And that's how I learned about Masdar, because this plant was built by Masdar and Sener, a Spanish company. So I heard about Masdar and I discovered United Arab Emirates, and I decided to apply, and I got a position as an assistant professor at Masdar Institute in 2013. And then Masdar Institute merged with Khalifa University in 2017. And finally, I created my startup company in 2019, which is called Ceramic Material. And I forgot to mention that I funded also the Masdar Institute Solar platform that you can see on this picture. So this is quickly my background. So today I will talk about consensus solar power and thermal energy storage. I will focus mainly on UAE because that's where I am, but I will give you some example of international projects, and I hope you will enjoy this talk. So first of all, if my slide wants to move, I will talk about some economical aspect and energy strategy. So UAE decided to deploy 50% of clean energy by 2050. So this 50% in the total energy mix will be composed of 44% of renewable energy, mainly solar in Abu Dhabi, because wind is not strong enough to deploy wind energy here. And then 6% of nuclear energy, which bring the total to 50%. So it's a very, let's say, ambitious target, and we will check that we are on track. So we have ongoing and some part operational, some big solar farm in Abu Dhabi and Dubai. So for example, on the left, you have a 1.2 megawatt solar farm, which was one of the biggest plant in the world when it was commissioned. So you see it's really huge, mainly photovoltaic panel in this case. And then we have a big project in Dubai, the Mohammed bin Rashid Al Maktoum Solar Park, which will be a 5 gigawatt solar park by 2030, if I'm not wrong. And this park combine concentrated solar power and photovoltaic. So UAE are really deploying renewable energy massively, which is very good. And so I did roughly some calculations. So today we have 27 gigawatts of power. If we take into consideration the announced projects, you can see that we have 3.2 gigawatt announced in Abu Dhabi for solar photovoltaic. We have 5.6 gigawatt of nuclear and 5 gigawatt in Dubai of solar. So if we add all this, we are at about 33.8% of clean energy in the total energy mix, which is still below the announced 50%, but of course we still have time till 2050, which is good because it's a good news. We may have some new projects, and why not concentrated solar power? So I will try to demonstrate that concentrated solar power is a good option for solar in the UAE. So I will use a lot the levelized cost of energy or electricity, LCOE. Basically, this is the cost, all the cost of your plant. So for example, if you take a car, if you want to do a comparison with a car, when you buy your car, the cost of your car is capital expenditure, CapEx. And then once you use your car, you will put fuel in your engine, you will change the tire, change the battery, go to services. So all this is a operational expenditure, OPEX. So you will have all these costs during the full time of the plan. So usually it's about 25 years. And you divide by the forecast energy you will produce with this plan. And you obtain a cost per kilowatt hour. And with this LCOE, you can compare different technology together. So on this graph, you see the comparison of different renewable energy. So you have here the LCOE in US dollar per kilowatt hour. And here you have the time, and you see, for example, for photovoltaic, a very impressive decrease of cost with between 2010 and 2020. So just to give you an idea, when I joined Masdar Institute in 2013, renewable energy were still expensive compared to other technology, but in 2017 we had really a decrease in cost in the range of the low cost of fossil fuel. So on this graph you see the fossil fuel range here. So you see that photovoltaic became very, very attractive around late, well, this is for the world, but in UAE it was in 2017 we had very impressive low cost for solar energy. And if you look at CSP, you see also a deep decrease in cost, even higher rate than PV, which is a good sign. Of course, we are still more expensive today than photovoltaic, but we will see that we have to compare apple with apple later on. So it's very promising. We see a deep decrease in cost, both in solar photovoltaic and concentrated solar power. So recently we have seen world records. So in April 2020 in Dubai, in Abu Dhabi, $1.35 cents a kilowatt hour, and recently in April 2021, 1.04 cents a kilowatt hour in Saudi. So clearly today, solar photovoltaic is the cheapest way to produce electricity in the GCC, with the solar resource in the GCC, including fossil fuel, which is remarkable because it means that in an oil and gas country, it's cheaper today to produce electricity with a solar panel than with a gas turbine, for example. All right, so what about concentrated solar power, CSP? Well, recently in September 2021, there was a bid in Chile. Sorry, that's my phone. I'm sorry about that. In Chile, we had a bid at 3.39 cents a kilowatt hour. Why so low? Because Chile is the best place in the world in terms of solar radiation. So that's explained how we can reach very, very low cost for CSP. So if you compare with the last bid in PV, 1.04 cents, we are roughly 3 times more expensive, okay? But as I mentioned, we should compare apple with apple. When you deploy a concentrated solar power plant, you have energy storage integrated. So we are talking about the dispatchable power. You produce electricity whenever you want. Whereas all this solar farm in PV doesn't include batteries, okay? So you produce only during day when you have sun, and therefore it's non-dispatchable power. So it's really important, my message today, we should not compare solar photovoltaic with CSP because CSP doesn't compete with PV, it competes against dispatchable power, for example, gas. So it's really important. I like this article from SolarPace's website. It's really important to mention that we are not in competition and we are even complementary, and I will try to demonstrate that today. So if you look at the electricity demand on the grid, usually we have 2 peaks. So we call that the camel curve. 1 peak in the middle of the day and 1 peak in the evening when everybody goes back home and switch on the light. So if we take the example of California, which is a state in advance in terms of deployment of renewable energy, well, they got a problem called the duck curve. So basically, why the duck? You see that instead of having this 2 peaks, you have only 1 peak in the evening, and you can see here the neck of the duck. So that's why they call that the curve. So here you see the electricity demand as function of time of the day, and they subtracted the power coming from photovoltaic. So you see in 2012, they had 2 peaks like in most of the country, and then they started to install PV like crazy. And so you start to shave the peak in the middle of the day and obtain this kind of curve to a certain point where you have 2 problems. The first problem is an overgeneration risk. So imagine that you have a nuclear plant that produces your baseload power, and so your nuclear plant is producing a constant power. You cannot go below that. And so imagine if your subtraction of electricity demand minus the PV goes below your baseload power from the nuclear plant. That means your solar energy that is produced from PV is useless, and so you have an overgeneration risk. This electricity is not needed by the grid, and as you know, when you produce electricity and you inject it to the grid, somebody has to consume it somewhere. If not, you risk a blackout on your grid. So California has a problem to get rid of this electricity, and what they do, they beg the state around them to get rid of this power. So imagine if you are an investor and you invested in a solar farm, while you are losing your money at this time of the day because nobody needs your power. And that's explained why energy storage is really important in this case. The other problem of the curve is the big ramp you will have when the sun goes down. All this big giant solar farm power is decreasing, and that's exactly when the second peak of the day, remember the camel, the second peak of the camel, is starting. So in a very short time, you have to put on the grid a huge quantity of power, and usually what people are doing if they don't have hydropower available, well, they are starting the gas power plant, and this is not good for environment, okay? So you see the 2 problems, overgeneration risk and the big ramp in a short period of time at the end of the day. Well, we believe that CSP with energy storage is a solution to this problem, because you will use solar photovoltaic during day because it's very cheap to match your first peak. And at the same time, you will charge your energy storage using CSP, or also you could charge it with PV as well. Now I will show you an example, but you charge thermal energy storage to answer the evening peak with the storage. And this is crucial for grid management if you want to deploy renewable energy at a massive scale like UAE is trying to do. So I think my colleague previously mentioned the option, but quickly, this is your solar resource. So you have 2 options. If you want to do a constant power, all the power that you have above your constant power, you store it and you discharge it at a later time in the evening or in the night. And that's how you could get constant power. Or the other option, which I believe is more attractive for the grid management, is to store all you can during the day and discharge in the evening peak while you don't produce during the day with the storage. So I'm not the only one to say that CSP and PV are complementary. DEWA, which is Dubai Electricity Water Authority, is deploying 5 gigawatt of solar, among which 1 gigawatt will be CSP and 4 gigawatt PV. Mazen in Morocco is doing also the same, deploying 1.5 gigawatt with 910 megawatt of CSP. So we really believe that we can have a combination of 2 technology to offer to our clients 100% sustainable solution without burning gas. If we look at this data from IRENA, which is an International Renewable Energy Agency, located, the headquarters is located in Abu Dhabi, in Masdar City. So this is a little bit old from 2018, but what is interesting is change of cost of electricity depending on the different technology. And if you look at concentrated solar power, you see that you had a cost reduction between 2017 and 2018 of 26%, which is a double of the cost reduction in PV. So it's very encouraging to see that the fact that, for example, China is entering the market and producing massively component and all this help to decrease the cost of a concentrated solar power plant. Now, very often I have the question, why don't we add batteries to PV? Yes, that's an option. You could add battery to PV and get a 100% dispatchable solution. But battery are very attractive for, let's say, small storage capacity. So if you need less than 3 to 4 hours storage capacity, then battery makes sense, and you should go for batteries because it's simple. With PV, you don't have moving parts. The battery will have to be changed, so they are not really performing well in a desert environment like Abu Dhabi. You need to have, for example, AC system to protect the battery. So thermal storage is more adapted to desert environment. But if you look at this study from the National Renewable Energy Laboratory, over 9 hours of storage capacity, then CSP is much more competitive than PV plus battery. You see here the projection, for example, for 2025, even with a decrease in cost of battery, CSP with thermal energy storage is still more competitive than PV. And that's the reason why we believe that CSP is complementary to PV for a 100% sustainable solar solution. All right, so now I hope I gave you some good arguments to, let's say, promote thermal energy storage. I will go through the different CSP technology that have been deployed all over the world. So you have two ways to concentrate the light. So we are using mirror to concentrate the light from a large surface to a small surface. And that's how we concentrate the sun and reach very high temperature at the focal point or focal line. It depends. You can concentrate on a line using, for example, parabolic trough or linear Fresnel, or you can concentrate on a point using a parabolic dish or power tower, for example, which are the main 4 technology on the market. If we consider linear concentration, the most mature technology is parabolic trough. So this is a cross-section of your parabolic trough. You see a parabola. So you have to be perpendicular to the ray from the sun. That's why we are using tracking. And so each ray that is coming perpendicular to the aperture of your collector will be concentrated at the focal point. If you extrude this, you have a line, and that's where you will place your tube. In the tube, you will circulate synthetic oil to collect the heat up to 400 degrees Celsius in this technology. So one example of parabolic trough in UAE is Shams Power, which is a joint venture between Masdar and Total, the French company. So Masdar owned 80% and Total 20%. It was built by Abengoa Solar, who later had some financial trouble, so they sold their share to Masdar. So you can see it's a very impressive plant built in the middle of the desert, 100 megawatt electric. Just some very interesting facts. To build it, they have to remove 500 million meter cubic of sand to make the land flat, because as you know, in the desert you have dunes, and to avoid the dunes to come back, they build 7-meter high wall all around the plant to protect the sand to come back inside the plant. And it's working well. From time to time, they have to remove sand along the wall, but the wall is really working well. Of course, we have to clean the mirror. We are using 2 million gallons of water to clean the mirror per year. But if you compare to the water that was saved by using the dry cooler, so I will come back to this, instead of using a cooling tower that consumes water, they install a dry cooler that is using air and fans to condense the steam in the power block. And so the quantity of water saved using this dry cooler is 200 million gallons per year, which is 100 times more than what we use to clean the mirror. So just to give you an order of magnitude, so cleaning the mirror is manageable. We have 5 trucks working every night using automatic brush to clean the mirror. And the plan is performing very well since 2013 without any major problem. So the particularity of Shams is that it's hybridized with natural gas. So there is no storage. And why there is no storage? Because Shams was planned in 2007, and the first commercial plant with thermal energy storage was inaugurated in 2008. And so I will come back to this after. So they already included 2 major innovations in Shams Power, which is a booster heater and the dry cooler. So the booster heater basically is used to increase the efficiency of the plant. Why? Because on the left you have the solar field that heat synthetic oil to about 393 degrees. The synthetic oil will go into heat exchanger to produce the steam for the turbine, and this steam will be produced around 380 degrees Celsius. After that, they burn a little bit of gas to superheat from 380 to 540 C, and this will, as you know, increase the efficiency in your power block. So, of course, the main part of the job is done by the steam generator and so by the solar field. So the quantity of gas is neglectable compared to the energy that is consumed here from the solar field to evaporate your water to steam. So it was a good idea to include the hybridization with natural gas, especially because a gas power plant was close by, so they already had the pipeline to bring the gas, so the investment was limited. The other innovation is a dry cooler. I will show you a picture after. So the dry cooler, as I mentioned, is saving a lot of quantity of water. And so this was the good option for this plant in the middle of the desert, because we don't have any water in the desert. So here you can see some picture of the steam generator. So it's a 3-step generator: preheating, evaporation, and superheating. So basically, how it works, this is a cross section. You have a pipe where the water is circulating, and around the pipe you have a synthetic oil. So you preheat the water here, and then in the evaporator, that's the contrary. So you have the oil in the pipe, and the water is around the pipe to let the water evaporate and get the steam. And in the superheater, it's again the contrary. The steam is under pressure inside the pipe, and the oil is around the pipe. So it's very conventional heat exchanger, but you have to be careful to never mix water with oil or on the contrary. Then this is some picture of gas heater from the plan. I already mentioned this. And here you see the dry cooler. So basically you have 5 meter in diameter fans and a series of fans in series and in parallel. So the steam will come, circulate in pipe, you will blow air, and by blowing air, you will condense the steam in the power block. So unfortunately, Shams doesn't include storage, but I can guarantee that if Shams was built today, they will build it with thermal energy storage, and more particularly the two-tank molten salt technology. So here you can see nitrate salts that are usually used in agriculture as a fertilizer. But if you increase the temperature up to 220 C, the salt will melt and become liquid, so you can pump it, and it's very convenient for a concentrated solar power plant. So you have on the left the solar field, conventional parabolic trough plant, using synthetic oil. The synthetic oil will go to the heat exchanger to produce the steam for the turbine. And during day, when you have a lot of energy, too much energy, one part of the oil will be sent to another heat exchanger where it will exchange heat with the molten salt. So you have a two-tank system. One tank is called the cold tank, but when we say cold, it's relatively cold because the temperature is 290 C. And so you pump the cold salts, take the heat from the oil, and bring the molten salt to temperature, in this case of 390. In the case of a tower, we can go to higher because we don't have the oil, we have a direct system. But basically you store this hot salt for the night, and at night you do the contrary. You pump the hot salt, go to the heat exchanger, transfer the heat to the oil for the turbine, and bring back the cold salt in the cold tank for the next day. So that's a conventional mature technology, which was, by the way, developed in the 80s in France, in the Themis power tower, which is close by to the giant solar furnace I showed you previously. And so here you see the first commercial plant that used this technology in 2008, which is Andasol 1. It's located in Granada, in south of Spain. And you can see here the giant tank full of 28,500 tons of nitrate salt. This tank are huge, 36 meter in diameter and 14 meter height. So you see it's really huge. And so with this storage, Andasol 1 can produce 50 megawatts of electricity during 7.5 hours during summer. So I will show you immediately some graph from this plant. So I don't need to explain that because I already explained it. So here you see the power production from Andasol as function of season. So I'm sorry, it's in Spanish because it's I got it from the Spanish plant, but invierno means winter and verano means summer. So you see that in winter, that's the blue line, we have a very small shoulder here. That means we are moving from the direct production to the thermal energy storage production. And you see that the duration of discharge is very short. Why? Because the solar radiation is much lower in winter than in summer. And you have to know that the plant is designed for the summer months. And you see that in summer, we discharge during 7.5 hours from the storage. Okay, so this plant is really the reference. Now, what's next? In the CSP community, we want to reach much higher temperature. And why we want to reach higher temperature? Because of the Carnot cycle. The higher the temperature, the highest the efficiency from heat to electricity. So we want to use different type of power cycle, for example, Air-Brayton cycle or supercritical CO2. And for that, we need to reach high temperature in the range of, well, for supercritical CO2 right now, we are around 715 C. But for air Brighton, we are talking about 800 to 1000 degrees Celsius. And in this range of temperature, molten salt cannot be used because nitrous salt above 600 C are degraded. And if we consider other type of salt, for example, chloride, we have a big issue of corrosion at this level of temperature. So many laboratories are working on chloride, for example, funded by US Department of Energy. But personally, I don't think that chloride will be an option in the future. So we need to find other solution to store heat at very high temperature in order to use this Brighton cycle and combine it with a steam cycle and reach more than 50% of conversion from heat to electricity. So to work at higher temperature, we can use a different CSP technology, which is called power tower or central receiver. So instead of using oil as a heat transfer fluid in the solar field, we directly use molten salt as heat transfer fluid and storage media at the same time. So basically you have heliostats, which are giant mirror that will redirect the light at the top of the tower, a reflectory which reflect the light at the top of the tower where you have your solar receiver. And so you will pump the cold salt at the top of the tower to collect the heat. And as the salt can go up to 600 degrees Celsius, well, in this case, we will operate at about 575 degrees Celsius. So you pump the salt at 290, go in the solar receiver, reach 575 and bring the salt in the hot tank. At night, when you don't have sun, you pump the salt, go to the heat exchanger, produce a steam for your turbine and bring back the relatively cold salt in the cold tank, waiting for the next day for the next charge. So this concept, as mentioned, was developed in France in the 80s and then was commercially demonstrated in 2011 by Masdar and Sener with a Toresol, with a Gemasolar plan owned by Toresol, which is a joint venture between Sener and Masdar. And to be honest, that's how I learned about Masdar and United Arab Emirates, because this plan was a real breakthrough in the CSP field. It was the first CSP plant producing 24/7, thanks to 8,500 tons of molten salt. So it's a 20 megawatt plant with 15 hours of storage capacity. Here on this picture, beautiful picture, you can see two important things. You see here a river. So the water of the river is used for the cooling tower in the power block. And also they build a big reservoir to collect the water from the rain. Of course, this is not possible in Abu Dhabi. So that's why the dry cooler is a better option. But as you know, the dry cooler will penalize the power cycle. Cooling tower is much more efficient for condensing steam. So here you can see data from Gemasolar in Spain. So it's 7 consecutive days. So you see here the solar resource. Of course, at night you don't have sun, so you have no source. But in red, you can see that we are producing almost constant power over a full week. So this was really a breakthrough in the CSP field because of a constant power production. Of course, this is during summer because the plan was designed for the summer time. In winter, it's not possible to produce a constant power in this case, but it was a real achievement at this time, and that gave me a motivation to apply to Masdar Institute, which was at this time the University of Masdar, and that's explain why I'm here today. All right, so this Gemasolar plan of 20 megawatt was upscaled with in the US with Crescent Dunes in Nevada in 2014, and this plant is 110 megawatts, so more than 5 times bigger than Gema Solar. I think we have reached now the limit for Power Tower because if you look at the configuration of the plant, the last heliostat here is very far away from the bottom of the tower, maybe more than 1 kilometer for sure, maybe 2 kilometers. And so it's very difficult after to concentrate the light very accurately in the receiver. And that's why you see now a new concept of multiple tower. So instead of having a giant tower, you will have several towers, but smaller tower, maybe 50 meters high. And so you have a company, for example, Heliogen, which is funded by Bill Gates, which used artificial intelligence to control small heliostat very accurately at the focal point. And so I believe personally that several small solar field with several tower would be a better option than a giant tower, especially because in UAE we have attenuation. In summer, in the atmosphere, we have humidity and a lot of dust. And so when the light is reflected from the heliostat, the last heliostat, it will have to go through this particle, and so it's attenuated, and nobody up to today measures this attenuation in real condition. So I think a multiple tower concept would be a better option to my point of view. So there is a big project at DEWA, as I already mentioned, 700 megawatts of CSP. So it will be composed of 3 parabolic trough of 200 megawatt each and 1 giant tower of 100 megawatts. So as usual, Dubai likes to build the highest tower in the world. You may know Burj Khalifa, which is the highest tower in the world with 828 meters. So for the CSP plan, they also decided to build the highest tower in the world with 260 meters. The previous one was Ashalim of 250 meters. So here you can see the picture of this tower in Dubai, built by Aqua Power and Shanghai Electrics. So it's completed. Now they are completing the solar field. At the same time, recently in November, they filled the molten salt tank with molten salt. So which means that the plant is really close to commissioning, because as you know, when they fill the molten salt, it will never solidify during 25 years, which is expected lifetime of the plant. All right, so this is the situation in terms of state of the art on the market, mainly parabolic trough and power tower using molten salts, either in indirect way or direct way. So when I joined Masdar Institute in 2013, I decided to create a solar platform dedicated to CSP and TES, because to my point of view, you cannot separate CSP and TES. TES could survive without CSP, but CSP cannot survive without TES. So we create this platform called Masdar Institute Solar Platform, MISP. And so this is a picture of a recent picture of the plan with the different projects we have developed. I'm sorry for the mess in front, but we are under construction. Apologize for this. So you can see we have different facilities. On the right, we have built an oil loop, which is using electrical resistance heater to warm oil up to 400 C. We use it to test the big concrete storage from Energy Nest, a startup company from Norway. We have a beam down concentrator. I will explain after what's the concept? We tested a molten salt receiver with MIT here. We have a new concentrator built by Wahash Solar, a startup from Dubai. It's basically a giant Fresnel lens made out of mirrors. We have two dish now. We have built another one here, 2 dish, and here we have a project with Azelio. I will come back to this in detail after. So we inaugurated the solar platform in 2015 in the presence of Dr. Sultan Al Jaber, who is now the Minister of State and CEO of ADNOC. ADNOC is, let's say, the most powerful oil and gas company in Abu Dhabi. We are showcased today at the UAE Pavilion. So if you come to visit the Expo 2020, you will see all the storage material we have tested there. So I will start to give you a summary of different projects I've been doing with my student or staff. So the first one was called SandStock project. So when I joined Masdar Institute, I see that we have a lot of desert sand all around us. So why not using sand as a storage material to collect the heat and store the heat? So we designed a receiver, and we went to France with my students at the 1 megawatt solar furnace. At the back side of the giant parabola, we have horizontal solar furnace. So you can see here at the back, you have one heliostat that is horizontal. And so this light will be reflected vertically inside the building where you have a hole. And inside the building, you have a parabola that concentrates the light at a focal point. So it's very powerful. And so we decided to make a flow of desert sand inside a conical shaped receiver. So as you can see here, the sand is coming and flowing inside the receiver where the light is concentrated. So this sand bed is under very high flux, and so the sand particles are collecting the heat. Of course, at the bottom you have a hole, so the sand can flow naturally by gravity, like in a sand hourglass. And so we tested 2 different designs. This was the first design. The first summer we went there 2 summers for summer internship. And this was the second design. So for example, in this design, we have found that the wind was blowing, and so the particles are so lightweight that they were kind of dispersed all over the place. So we decided to include this into a quartz tube to protect the receiver from the wind. And so that's the second design we have made and tested there. So you can see here yes, can you hear me? Hello, can you hear me?
Yes, sir.
So sorry, Jacob, I'm presentation now. I call you later. So here you can see the cold tank where we have the sand. The sand is flowing through this the light is concentrated through this quartz tube, and the sand fall down into the receiver that is here and collect the heat. So using this small design, we reach more than 600 C with desert sand, and almost 900 C using silicon carbide particles, which are black, so which absorb much better the energy than the desert sand. So this is really trendy in the community. We call that particle receiver. Usually people are using tower, but in our case, we use a beam down configuration because we want to upscale that using our 100 kilowatt thermal beam down. So if you are interested in this project, we have 2 publications, one in applied energy and one was in a conference. I don't remember. Yeah, the conference was here. Oh yeah, it was Solar Bases in 2014. All right, another project in collaboration with Energy Nest, which is a startup company from Norway. We tested concrete storage. As mentioned previously, concrete is a very interesting material because it's cheap. You can cast it everywhere in the world. You don't need very, let's say, qualified manpower to cast concrete. And so if you go in, for example, in summer in a parking in Abu Dhabi, it's really hot because all the concrete is storing this heat. So we developed this oil loop, which is certainly a upscale version of what my colleague presented previously. This is a 100 kilowatt electrical heater here. You have the expansion tank here. Here we have a dry cooler to simulate the discharge. And here we have 2 pumps. So basically this is made to reproduce hot oil at, let's say, 400 C to simplify, exactly like you would have hot oil in a parabolic trough, in a commercial parabolic trough, except that you don't need kilometers square of land for installing the solar collector. So keep in mind that here we want to test the storage unit, which is here. And so the goal is to charge and discharge as fast as possible. So we did almost 1 year of experiment, charging during day, discharging during night. So here the storage pilot, basically we have concrete columns, so 5-meter high columns. They are vertical in this pilot, but in the commercial, now they are horizontal. Doesn't change much. You have a U-shape, double U-shape heat exchanger embedded inside the concrete column. So the hot oil is entering here and exiting here, and entering here, exiting here, and that's how we charge the storage system. So we have done 280 cycles without any degradation of performance. You can see here some results from the experiment. Very importantly, at the end, we dismantle part of the column to cut it and check that we have still a good contact between the steel and the concrete, which is very important. And so recently, Energy Nest raised $130 million thanks to this pilot. So now they are commercializing this technology, and their main market is not really CSP, but more waste heat recovery in industry. For example, they are deploying a commercial unit in the Netherlands in a steel factory. So if you are interested in concrete storage, please refer to this paper published in Journal of Energy Storage. I will share my presentation with you if possible after, if you want to have all the reference. Let me take a drink. Sorry. So this project was a collaboration with MIT in the US. MIT published in 2011 a paper called Concentrated Solar Power on Demand, or CSPOND, which was testing 7 liters of molten salt in a solar simulator. So when I joined Masdar Institute in 2013, I contacted Professor Slocum, who published this paper, to upscale from 7 liters to 4 tons of molten salt. So that's the world's first direct absorption molten salt receiver tested in real onsen condition. So basically we have a tank which is open at the top. On top of the tank we have a secondary concentrator. that concentrate even more the light coming from our beam down. And so inside the tank, you have a mixing plate and a divider plate. So the divider plate is here to separate the hot salt from the cold salt. And therefore, we use one single tank instead of two tanks, like in the commercial two-tank technology. This plate can move up and down depending if we charge or discharge. So we have also a mixing plate because we realize that the salt, even if it's transparent, it's not 100% transparent. So when the plate is very low, we had difficulty to reach the bottom of the salt, and so we install a mixing plate in order to homogenize the temperature. But basically, the advantage of this concept is that you don't need to pump the salt at the top of the tower. You bring the light directly into the volume of molten salt. You don't need pipe, you don't need pump. So you don't have any problem of thermal shocks. For example, in the morning when you start the plant, you have to preheat your receiver in order to circulate the salt to avoid freezing or crystallization of the salt. In our case, we don't need to do that. Even at night in the tower, you have to drain the receiver to avoid crystallization. Again, in our case, we just close the lid. You see here the lid. We close the lid of the tank, and we don't have any problem of thermal shocks. So using one tank instead of two tanks, we also cutting the cost. So we started to test this system in June 2017. At the top of the beam down here, so basically you have the heliostat on the ground. The heliostat reflects the light at the top of the beam down. And here, instead of having your receiver, you have secondary mirror that redirect the light down on the ground, hence the name beam down concentrator. And so this cone of concentration will enter into our secondary concentrator here, which is made of polished aluminum. And so it will enter into the tank where you have the molten salt. So we have located a camera, a CCD camera at the top that can look into the tank, and that's the view you have on the right. I don't know if the video can work. Change to yeah, okay. So here you can see the mixing plate that is bringing a chunk of salt that is not molten yet. This cost us several thermocouple because we saw that all the salt was molten, and so we started to move the plate, but our probe were embedded inside some solid salt, so we broke some of them, but we learned a lot by doing this pilot. So you can see clearly the salt that is looking like water, but it's working very well. And so here I will show you some results. So at the beginning of the day, the divider plate, it's at, let me go back to the laser point. The plate is at the top, so you have a small layer of molten salt. We start to focus at T0. Here it was about 9 o'clock in the morning. And you see that the temperature is increasing to 450. In this case, we set up 450. At 450, what will happen? The plate will move down a little bit. And so on the side, you have space between the end of the plate and the wall of the tank. So some cold salt can come from the side and mix with the hot salt. That explains this decrease in temperature here, because you are mixing with cold salt. Then you have some solar flux coming, so the temperature raise again. And here, when we reach 450, again, we move down the plate, okay? And that's how you end up with hot salt at the top, cold salt at the bottom. And you do that all day, so your part of hot salt will increase till a certain point here. You see that we have difficulty to reach the bottom of the tank because the volume of salt is not perfectly transparent like water. So that's why we decided to include a mixing plate. And so you see, we move the mixing plate, and this has an effect to homogenize perfectly the full volume of molten salt. And after that, we see that we are able to reach almost 500 C in this case. So we tested this up to 500 degree, not yet to 550 due to time constraint, but this is in our plan for the future. Another way to represent this result is to plot the height of the tank as function of temperature. So you see at the beginning of the day at 8 o'clock, this is here, you have a temperature of 350 in the tank, homogeneous. And then at the end of the day, at 4 o'clock, you see that all the useful volume of salt is at, let's say, 480, something like that, in this case. Okay, so we are able to charge the system using directly irradiated molten salt, which was the first time demonstrated in the world. So we are really proud of this project. We took a lot of time to publish this result because, trust me, it was not an easy project. First, we have a big plan, 100 kilowatt thermal. We had to refurbish all the beam down. And then we had to design the system, build it, and experiment. So it took a lot of time to end up with this result. But now it's published in Solar Energy, and the paper is called Dispatchable Solar Power Using Molten Salt Directly Irradiated from Above. So I encourage you to go and check this paper if you have interest in new way to store energy in molten salt. Which bring me to, I think, my last project. I have another one, so 2 more. This one is a collaboration with Azelio, which is a Swedish company, and they have developed the first, to my knowledge, the first commercial high temperature latent heat storage solution. So basically, we are doing electrical thermal energy storage. So instead of using CSP to charge a system, we will use electricity from solar PV. So you see at the bottom, we have a map. The solar platform is here. This is the Azelio pilot, and we're going to install 500 kilowatt of solar photovoltaic panel. This electricity will come in this tank and melt a metal alloy, which is aluminum silicon, using electrical resistance heater. So during day, we melt the alloy, and at night, this alloy will naturally solidify and release the latent heat. So I will not enter into detail because my colleague already explained latent heat storage previously. Once we have recovered this heat using liquid sodium as heat transfer fluid, we inject it into the Stirling engine, which is the black box you can see here, to reproduce the electricity. So if you make an exergy study of the system, it makes no sense for the planet. I mean, you don't want to degrade, let's say, valuable electricity into heat to convert it again to electricity. So if you ask me my point of view as a professor teaching thermodynamics, I would definitely shout on this kind of project because the exergy is not good. However, if you look at the economics of this, with cheap solar PV at $1.04 a kilowatt hour, then it gives a lot of attraction for this kind of system. And that's why we are testing it, because it's a viable, cost-effective option to store electricity. And for example, in California, I show you the duck curve. Rather than paying their state around them to get rid of their electricity, they should better store it using this kind of system. So the system is under commissioning right now and should be operational at the end of, let's say, beginning of January, with an official inauguration during World Future Energy Summit. I think it will be on January 18. So if you are around Abu Dhabi in January, please feel free to send me an email, and you are welcome to come and visit this pilot. So it will be the first clean power production at night of Masdar City. Masdar City is a sustainable city in the middle of the desert. So we are again really proud of this project, and very interesting. A lot of things to learn in this system. Here you have a paper from my previous postdoc about the compatibility of the metal alloy and the containment. As you know, metal alloy at high temperature are highly corrosive, and so we worked on a special coating to protect the container from corrosion. And finally, I will show you my baby, because this is my thesis work that was recently, let's say, accomplished or finished with the world first 100% recycled thermal energy storage ceramic. So basically, if you look at high temperature energy storage, you don't have 1,000 options. You have particle receiver, like I show you with desert sand, or you have ceramics. Ceramics, conventional ceramics like silicon carbide. You have here honeycomb structure, which was tested, for example, at Jülich in Germany. So it's silicon carbide. It's very expensive, maybe $5,000 a ton, something like that. So thermal energy storage is not viable using ceramics. So during my PhD, I worked on industrial solid waste that are recycled into low-cost ceramics. And it ended up with our startup company called Ceramic Material with S. Ceramic is an acronym for Sustainable Energy Recovery and Manufacture Industrial Ceramics. And so what we do, we take industrial solid waste that have no value, and we convert them into value-added ceramic products in the technical ceramic market and in the construction material market. And so this is Flora, our first commercial product that is made in France, designed in Abu Dhabi and made in France. You can see here our production in France. And so this ceramic can go up to 1,250 degrees. It's 100% recycled by using different waste. And so you can use it in packed bed storage. Basically, you see the tank here. You use hot air as heat transfer fluid. And so you will charge your storage with air and discharge your storage with cold air. So we have two clients. The first client is Store Energy, which is a company from Serbia. They are testing, they tested already 300 kilograms with the CIEMAT laboratory at Plataforma Solar de Almeria. And now they are testing 24 tons with their solar pilot. And then we have Heliogen. I already mentioned them. This is the first CSP company backed up by Bill Gates in California. And at the time we talk, 4 tons of Flora are on the boat to be tested in the coming months in US. So with this, I'm done with my presentation, and I thank you for your attention, and I will be happy to answer.
Thank you, Professor Nicholas. Very this informative and very excellent the presentations we had. This nicely presented, and I think I hope that the participants will be benefited with with these presentations. Just basically in the area of the CSP and related with the solar, this thermal energy storage, and this wonderful work you have done for this, the recycled ceramic. So congratulations to you.
Thank you.
Now, I think this I can. It's 1 minute or 2 minutes are there. If any questions from the participants, 1 or 2 questions we can have. Participants, if no questions, then
If anyone
yeah.
have any question, you may ask.
I think we have question in the chat, right?
Okay, yeah, just I read that it's question from Himanshu Kumar. That's that curve is at California, also like our country. How demand side management is being taken care there?
The curve is at California, also like our country. How demand side management is being taken
care there.
Okay, so basically, when they have too much electricity, what they do, they give it to other states around them. So they are losing money because rather than having a blackout on the grid, as you know, if you inject electricity, somebody has to consume it somewhere. So if you don't consume it, you risk a blackout and lose your grid. So it's better to get rid of this electricity to your neighbors. But it's a huge problem in California, and that's why energy storage is really booming there, because they are in advance in terms of deployment of PV, and I'm sure you will have a similar issue in India as well. So we have to take care of this problem by proposing energy storage solution.
One more question is there.
What is the effect of this cyclic uses on the recycled ceramics which you have talked about?
What, can you repeat your question? What is what, sorry?
What is the effect on the heating capacities, heat storage capacities of the recycled ceramics which you have talked about in the last?
So you are talking about the CP, right?
Well, I think he's asking that means what is the heating capacity of this new material in comparison of other ceramic?
So you are talking about the specific heat. So what is important, in fact, is not the specific heat, is MCP delta T. So basically, if you need a good density, you need a good specific heat, and you need a high delta T. Okay. So with our ceramic, you have a slightly higher MCP delta T than with conventional ceramic from, for example, delta P2 from Saint-Gobain, which is the world leader in ceramics, technical ceramics, at a cost that is significantly cheaper. So we're talking about more than 50% cheaper than our competitors. Does that answer your question? I can share with you the data sheet if you want the exact value.
There's one more question. There's 2 more questions are there. I think, why is concrete preferred over the sensible heat storage material like sand, rock, especially for high temperature applications?
Okay, so first of all, concrete is not preferred for high temperature. Concrete is limited at 400, 450 maximum. So concrete is not in competition with, for example, ceramics. This is not the same level of temperature. Why we prefer concrete than sand or rocks? Because it's very simple to implement. So you have a pipe and then you will cast concrete around it. So it's very simple to design your system and to exchange the heat between the synthetic oil and the concrete. However, it's performing not as good as molten salt. So it's very important to understand the difference between molten salt and concrete. In molten salt, you have your storage capacity, which is the size of your tank, and then you pump your salt in a small heat exchanger, which is your power. Okay. In concrete, if you want to increase your power, you will need, and your storage capacity, you will need to increase everything, the volume of concrete and the volume of your heat exchanger, because the heat exchanger is embedded inside the concrete. Whereas with molten salt, you can increase the storage capacity by having a larger tank and don't touch your heat exchanger. Okay, so when you pump the molten salt, you will have a constant temperature in the heat exchanger till the end of your tank. So this is very, very appreciated by the steam for the turbine, because we like to have a constant temperature. When you discharge from the concrete, each time you pass inside the concrete, your temperature will decrease. So your power will decrease with time. And so your temperature also will decrease with time. So you will have to adapt your turbine to your steam production. So concrete is not better than molten salt, and I don't think we can beat molten salt at this level of temperature. However, it has other advantage like cost is cheaper. Also, you don't have the problem of freezing because the concrete is solid and will stay solid. So for example, if you want to go on vacation at the solar platform, we can leave our concrete storage, nothing will happen. Whereas with the molten salt, if we go on vacation, the salt will crystallize and we will need 2 weeks to remelt it. So you have some advantage like this. Of course, in a commercial plan, you will not go on vacation, so you don't have this problem. But at
right.
Level,
Thank you, Professor Nicholas. Actually, we have few more questions, but I will forward those questions to you, so that you can.
Sir, can I have one question?
Quickly, I don't know how much time you will take. Ask the question. You can quickly.
Sir, it's just a simple question. Can I ask?
You can ask, please.
Sir, how much energy we have to use in order to keep the molten salt in liquid form overnight?
That's a very good question. So basically, when we the advantage of our concept was that we melted the salt directly with the sun, which is not possible in a conventional commercial 2-10 molten salt system. As you know, in the commercial plant, we use an electrical heater to melt the salt for the first time, or even gas, depending on the plant. And then you will never crystallize it again. In our case, what we did, we put the mixing plate up, we put a small layer of molten salt, and at the bottom of the tank, we put electrical resistance heater, not to melt the salt, but to keep the tank warm, because we don't want, when the salt is molten by the sun, it will flow at the bottom of the tank. If the tank is cold, it will crystallize. So we just put electric resistance heater to keep the temperature above the melting temperature of the salt, but we use only solar energy to melt it. So the quantity of electricity we used during the initial melting is really negligible compared to all the energy coming from the sun to melt the salt. And after that, we didn't use electrical resistance from one day to another. They are just there in case we have, for example, 2 or 3 days of cloudy day, which doesn't really happen in Abu Dhabi, but in case, then the electrical resistance will be here just as a backup in case, but we never use it during all the experimental campaign.
Okay, so I hope that you might have got the response. And thank you very much, Professor Nicholas, that you have very nicely responded the query of the participants, and I think it's clear. And if still they have more questions, more queries, so they can directly interact with the Professor Nicholas, or those queries can be sent to us so that we will request to Professor Nicholas to respond that. And thank you very much. And now for this session, I request Dr. C. Suresh so that he can just brief out these discussions or the presentations by the participants just in a few 3-4 minutes. So Dr. Suresh?
Yes, sir.
Can you highlight the things we are discussed in this?
Thank you, Professor Saini.
Yeah.
Yes, sir. Thank you very much, Professor Muthukumar and Professor Nicholas, for your valuable presentation. Professor Muthukumar has presented importance of renewable energy resources and also the working principle of different thermal energy storage systems. And also he has discussed different thermal energy storage systems and also the different storage materials that have been used in different thermal energy storage systems. And also he shared his experience about metal hybrids based thermal energy storage system and its various aspects, technical aspects. And further, he has discussed the different factors that have to be considered during the design of thermal energy storage system and also the design procedure. Further, the details of experimental setup that has been developed in IIT Guwahati, he has also shared with us, and also the different configurations of storage tanks which will affect the performance of the system is also discussed. Further, different heat transfer enhancement techniques, that is encapsulation of PCM, and also the introduction of novel films to improve the performance of the system is also presented. At last, he presented the global status of solar thermal power plants with the integration of solar thermal energy storage. Further, once again, thanks Professor Muthukumar, and also Professor Nicholas presented about the energy scenario of UAE and also the levelized cost of energy of different renewable energy resource system he has presented, and also the different concentrated solar power technologies also discussed. Further, operation of parabolic concentrated solar power plants is also further he has explained in briefly, and also the integration of two tank storage system with the CSP is briefly explained. Further, how the efficiency has been increased with the introduction of different cycles, and also the research and development that have been carried out in UAE is also he is explained, and also the different thermal energy storage systems integrated with the CSP plants in different regions is also discussed in clear. Thank you very much, Professor Rolet Muthukumar.
Thank you, sir, for concluding the session.
Yeah, thank you, Dr. Suresh, and I'm very thankful to Professor Nicholas and the Professor Muthukumar that they have nicely presented and the very excellent presentations they have put. And now we just I request to Siddhita that take over the charge. Thank you. And
Thank you.
yeah.